Hello students, welcome to this video pertaining to the last month preparation strategy for the upcoming GATE 2025 exam in the mechanical branch. This is Sekhar from Msigma Gokulam. I've got more than 25 years of GATE teaching experience. With all my experience, I would like to give some very important tips what to do in this last 30 days left over for the GATE examination. Approximately around 30 days are there to write the GATE mechanical. So what to do and what not to do, the very important strategic points, insights, particularly for the GATE aspirants, I am going to discuss in this video. All of you must have been doing, preparing very well for the last 5 or 6 months, eagerly to write the exam, waiting to write the exam in another 30 days. So what to do in these 30 days? That is the very important points I would like to discuss here. The main thing what you have to do here is, there are certain areas, certain pockets where the questions are definitely, damn surely will be asked in every GATE examination. Certain areas are more important. If you just ask any GATE topper or any very GATE good ranker, he will definitely say, look into those areas, you don't have to look into these areas much. So that kind of a distinguishing, what are those specific areas where you have to give focus more, and where you can definitely expect the questions from those pockets in each subject. That is not only true in the mechanical, it is true in every other branch also. So I'm pertaining to the mechanical branch. I would like to take each subject one after another, and I would like to put up some important insights where you have to focus more. And after identifying those important areas, we have to make a short notes, small précis notes, like short notes, short important points, and a small chits you have to write. Okay. And just before 2 or 3 days, 1 or 2 days before the exam, you have to revise very quickly each and every subject, the relevant formula, the pertaining formula, the underlying concept behind the each topic and behind each problem. All these points I would like to discuss in this video. And first let me broadly divide the syllabus into 3 areas. You're all known, the core mechanical contains 3 areas: thermal and fluid sciences, and manufacturing and industrial, and as well as the design and applied mechanics. So I will consider the first thermal and fluid sciences, where I would like to focus by considering each and every subject, what are those specific areas we have to give extra attention. So if you just look at this thermal and fluid sciences stream, where are the questions are most likely to be asked, which subjects you have to focus more. Actually in this thermal and fluid science, fluid sciences stream, we got actually 5 subjects, but the 2 subjects are condensed into one. The main important subjects are fluid mechanics, thermodynamics, heat transfer, and the power plant, RAC and IC. So these are the areas. Power plant, RAC, IC, in fact all the 3 subjects he has put into one stream, one chapter actually. So coming to the FM there, the very important subject in a fluid mechanics, you can expect approximately 7. Generally, general weightage will be around 7 marks, 6 to 7 marks, but there are certain areas where you have to give extra attention. What is that areas? Generally in the fluid mechanics syllabus, the first chapter will be fluid properties, right? All the viscosity, surface tension, capillarity, and all the specific weight, etc., etc. But among all those topics, the most important question that might likely to be asked will be about the viscosity. Viscosity, definitely one question may come as such. Okay, maybe usually in the 1 mark. Generally you will be giving something like an inclined plane, a slab, a block will be sliding, there is a thin viscous film. Okay, given the known viscosity, certain dynamic viscosity in Pascal second, we may need to calculate, or sometimes we need to, will be given, or sometimes we need to calculate what will be the velocity which is sliding. The gap will be given. Okay, the gap will be given between the block. A block is sliding on a thin viscous film. So the questions may be asked regarding this area. Give more focus there, where you have the dynamic viscosity mu and as well as the kinematic viscosity nu. Okay, in meter square per second. Fine. So this is one important thing we have to give in the very first chapter. And another important chapter where you have to give very important focus is the fluid statics. In the when you come to the fluid statics, the main thing what they will ask will be the hydrostatic force. Not many cases are there, just for the vertical lamina, horizontal lamina, inclined lamina, and hydrostatic forces on immersed surfaces. Generally here the certain complicated geometries will be there, something like this. For example, there is one cylindrical log, one side of the log, a cylindrical log, okay, there is a water. What will be the hydrostatic thrust on that log? Maybe a horizontal thrust, or you may be asked to calculate what is horizontal thrust and what will be the vertical force. So the questions may be asked on the hydrostatic forces are curved surfaces. Actually, in fact, he has asked in GATE 2004, he has asked in GATE 2013. In GATE 2013, he has asked one inclined plane carrying water on one side. So what should be the minimum weight of the block so that it will not get lifted up by the water force acting on this from the left side. This is all water. So this is an inclined force on the inclined plane. So the case of it is a case of the force on inclined plane, flat plane. You will be given the angle theta there. What will be the minimum weight of that inclined plane or the inclined plane body? On one side of that will be exposed to the water. So the questions may be asked in the second chapter on the hydrostatic forces. And in that chapter there is another important topic is also there, called as the buoyancy. Apart from the hydrostatic force, there is a buoyancy and flotation. The conditions of static equilibrium. The conditions of equilibrium in a completely immersed body and a floating body. In fact, as far as the buoyancy is concerned, the main important principle we have to remember is the Archimedes principle, right? Whenever a body is floating over a liquid or submerged inside a fluid, there will be an upthrust acting on the body which is equal to the weight of the liquid displaced by the body. Okay, so as long as you are very quite aware of that principle, you can solve any question given in the buoyancy. And for a completely submerged body or a floating body means ship. Completely submerged body means a submarine or a balloon floating in air. It is a completely submerged body. So for a floating body, for a completely submerged body, what are the conditions of equilibrium? Okay, there will be stable equilibrium, unstable equilibrium and neutral equilibrium. What are the conditions? For a completely submerged body, the relative positions of the center of buoyancy and the center of gravity will decide the condition of equilibrium. Whereas for a floating body, the relative positions of the meta-center and the center of gravity, the relative positions of the meta-center and the center of gravity will decide the condition of equilibrium for a floating body like a ship or a boat. When for a completely submerged body like a submarine or a balloon, the relative positions of the B and G, center of buoyancy and the center of gravity, will decide the condition of equilibrium, whether it is static, whether it is a stable equilibrium, whether it is an unstable equilibrium or a neutral equilibrium. So you have to remember that. You have to write a small see, for the entire hydrostatic forces, fluid statics, for entire fluid statics, we can just write all the important points on one page. The main three important points are there in the fluid statics. One is regarding the hydrostatic forces. Second thing regarding the manometry. Another important thing is the manometry, pressure measurement. Some arbitrary things may be given like a U-tube manometer. A U-tube manometer connected, one limb is carrying the, one side you have the water, one side you have the water or there is some other oil there. Over that there is some other oil, and you have the different fluid here, you have a different fluid here. Okay, so what will be the pressure at this particular center of the balloon? So that the simple manometry equation, how to write that, if you know, yes, practice the problems there. In the hydrostatics, three important topics are there: manometry, hydrostatic forces or immersed surfaces, and the buoyancy and the flotation. In the buoyancy and flotation, we should know what is meta-center, what are the relative positions of meta-center and the center of gravity will decide the condition of equilibrium. That is all about the fluid statics. So coming to the most important chapter in FM, the most important, I can say single most important chapter in fluid mechanics is fluid kinematics. fluid kinematics. This is a very important thing, because in the fluid kinematics very often the questions will be asked. Why? Because it is something connected with the mathematical expression of the fluid flow. Okay, we have, first of all we have to decide what is the meaning of the streamline, path line, streak line. Okay, that is number one. And velocity potential function, stream function psi, velocity potential phi and stream function psi. So the definitions of that, and what is the definition of the streamline, what is the equation of the streamline. Most important problem in the FM questions will be to getting the equation of streamline. How to get the equation of the streamline from given flow field. Like generally every flow field will be given in terms of the three velocity components. U, V, W are the three mutually perpendicular velocity components for the velocity vector of the fluid. U, V and W are the three mutually perpendicular, the components of the absolute velocity V of the fluid. Okay, you will be given this flow field and you are required to calculate what is the equation of the streamline. And we all know that the equation of the streamline begins for a two-dimensional flow. It is V by U. We have to begin from here and keep integrating that to get the equation of the streamline. And streamline, you all, in fact, streamlines, and which is a streamlines are a constant streamlines for which the psi is constant, and equipotential lines for which the phi is constant, they are orthogonal to each other. They cut orthogonally everywhere in the flow field except at the stagnation points. So we have to give more focus for this chapter in the FM. In fact, when I say more focus in the sense, we have to know what is the continuity equation in three-dimensional flow. For three-dimensional steady incompressible flow, dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. This is the three-dimensional continuity equation in a differential form. Continuity equation meant for the steady incompressible flow. Okay, three-dimensional steady incompressible flow. This is also given as the divergent V is equal to 0. Right. So and from that, if you are given any two velocity components, we can calculate the third component by substituting in this continuity equation. Continuity equation is after all a law of conservation of mass. Entire fluid mechanics, particularly fluid dynamics, when the fluids are in motion, the entire analysis of the fluid flow motion can be simply condensed into three conservation rules. One is the conservation of mass or the continuity equation. Second thing is the conservation of the momentum or the Newton's second law of motion applied to a fluid flow, which is also example is Navier-Stokes equation of motion, Euler's equation of motion. These are all the conservation of linear momentum. Okay. First thing is the conservation of the mass, which is also called as the continuity equation, which can be written in a finite form also. Whenever there is a fluid flow is happening, if the flow is steady, mass flow rate remains constant. That is, for a compressible or incompressible fluid, rho a v is constant. But if the fluid is incompressible, by default the density of the fluid is constant, which means if the fluid is incompressible, AV is constant. If the fluid is incompressible, AV is constant, because density is constant for the incompressible fluid like water. Water can be considered as an incompressible. All the liquid flows by default can be considered as the incompressible flows. In fact, for that matter, even the gas flows can be considered as incompressible if the velocities of the gases are relatively low. Okay. If the velocities of the gas flows are relatively low, even the gas flows also can be treated as the incompressible. Of course, there is a criteria, Mach number. Mach number is the criteria. As long as the Mach number is less than 0.3, as long as the Mach number of the fluid flow is less than 0.3, any fluid flow, whether a gas or a liquid or a vapor, can be treated as incompressible. Okay, only when the Mach number crosses 0.3, the domain of compressibility effect starts, where the density changes, pressure changes become very significant. Of course, that you would see only in case of the high velocity gas flows or vapor flows. That particularly in a convergent, divergent nozzles, what you see in a steam turbines like Delaware nozzle is a supersonic nozzle. Definitely the Mach number matters there. But for low velocity flows, whether it is a gas or a liquid or a vapor, does not matter. As long as the Mach number is less than 0.3, we can brand the flow as incompressible, and we can treat the density of the flow as constant. So AV is constant, we can bluntly write for the incompressible flow, rho AV is constant if the flow is compressible. This is general format of the continuity equation for steady flow. Of course, conditions apply. When you can write this for a steady flow. What do you mean by steady flow? Things will not change with respect to time at a given particular point. Okay, so most of the occasions, 99% cases, all the fluid flows we treat them as the steady flows. I don't say that unsteady flows are not there. Unsteady flows are there, but they are relatively low. Actually, the flow of the steam through a steam turbine is a steady flow. The flow of the water in a convergent divergent nozzle, it is a steady flow. Flow of water through a venturimeter is a steady flow. Okay, so in the kinematics, why the kinematics chapter is so important is, in this kinematics chapter we would like to show the fluid flow in a mathematical form through the continuity equation, through the velocity potential, through the equation of the streamline. So we have to understand, we have to give more attention. If you have not done until now, at least pay attention now for that chapter called fluid. Take my word, fluid kinematics is a very crucial chapter where you can definitely get the questions. Maybe on the velocity potential. What is the meaning of the velocity potential? Suppose that if you are given some velocity potential or a velocity components may be given. Some velocity components may be given. We are required to find the velocity potential function. Given the velocity potential function, we have to calculate the stream function. Given the stream function, we have to calculate the velocity potential function. What do you mean by irrotational flow? What do you mean by Laplace equation? Laplace equation is there, right? This is a Laplace equation meant for the irrotational flow of the Laplace equation. Any flow which satisfies this Laplace equation can be branded as the irrotational flow. Conditions for irrotationality. In one of the GATE examination, I guess it is 2008, he has asked about, he has given the 3 flow fields, he has checked which of them is the irrotational flow. What do we have to do? We have to find out the phi and check whether the flow is irrotational. If it satisfies this Laplace equation, this is the Laplace equation, right? If it satisfies this Laplace equation, we can treat that flow as the irrotational. If it doesn't satisfy, flow is rotational. And of course, there is another way also. A fluid flow can be called as irrotational only if all the 3 rotation components, omega x, omega y and omega z. There are 3 rotation components, omega x, omega y and omega z. When all the 3 rotation components about the x, y and z axis become 0, the flow can be treated as irrotational for the 3-dimensional. If it is a 2-dimensional flow in a xy plane, we don't have to check all the things. If it is just sufficient to check the omega z, if you just check the sufficient to check the omega z is equal to 0, then automatically the 2-dimensional flow can be treated as irrotational. Generally, in the GATE questions papers, most of the times you will give the 2-dimensional flows. 3-dimensional flows rarely will be asked. Mostly it will be given 2-dimensional. If the velocity function given carries the t, time t, that means the flow can be treated as unsteady. Okay. So most of the questions revolve around these very fundamental concepts pertaining to the fluid kinematics. We have to learn what is so in the kinematics chapter, what we have to learn? We have to learn about what are the various types of flow, number 1. You have to classify the flows: compressible, incompressible, laminar, turbulent, steady flows, unsteady flows, rotational, irrotational, 1-dimensional, 2-dimensional, 3-dimensional. We have to classify all the fluid flows properly. We have to understand each and every definition of all the types of fluid flows, and then we have to understand what is how to indicate the flow field by the velocity, by giving the velocity V is equal to Ui bar plus Vj bar plus Wk bar. I bar, J bar, K bar are the unit vectors along x, y and z directions. So you have to understand the velocity field, and then you should know what is the definition of the streamline, what is the, how to write the equation of the streamline, what is velocity potential, what is stream function, what is Laplace equation, what is the meaning of continuity equation. So the questions, most of the questions move around this in the FM, particularly in the kinematics chapter. That is slightly tougher chapter because it is something involves mathematical integration, differentiation, etc., constants of integration, getting the constants of integration from the given boundary conditions. It is slightly mathematically, the concepts are required, integration, differentiation, etc. But for that, if you understand thoroughly the definitions, you can easily solve them and get the, definitely take my word, you will get minimum 1 to 2 marks in that particular chapter only, okay, in the FM there. Right, and coming to the next chapter in the fluid dynamics, coming to the very important things, fluid dynamics. When I say dynamics, obviously the Newton's second law of motion is involved. What is when the fluid, when you're talking about the fluid dynamics, we are talking about Newton's second law, F is equal to ma. Okay, this is the equation when it is applied to a fluid flow by considering the inertia force, gravity force, pressure force, and viscous force. When you consider all these forces, if you write it for a fluid flow, then what you get is the Navier-Stokes equation of motion, which is the law of conservation of Navier-Stokes equation of motion, which is the law of conservation of momentum. And after all, Newton's second law of motion itself is the law of conservation of momentum. Law of conservation of momentum. If you neglect the viscous forces, pressure, if you neglect the viscous forces, if viscous force is 0, that means you are assuming the flow as inviscid. You are assuming the flow as inviscid flow. What do you mean by inviscid flow? We are assuming that the fluid has no viscosity. Is it practically feasible? No. Every fluid has got more or lesser viscosity. Some has got more, some have got lesser, but even the gases have got also, even the air has got the viscosity. So if you make the viscosity of the fluid is 0, then if you write that means you are considering pressure force, gravity force, and of course inertia force anyhow will be there. This is a MA, if F minus MA is equal to 0, that minus MA is called as the inertia force from the D'Alembert's principle. So if you consider the pressure force, gravity force, and the inertia force, and such conservation of motion is called as the famously known as Euler's equation of motion. So Navier-Stokes equation of motion and Euler's equation of motion, same principle, but only difference is in the Navier-Stokes equation of motion we consider the viscous forces, in the Euler's equation of motion we don't consider. So that is that different distinguishing must be done, and when you write the Navier-Stokes equation of motion, Euler's equation of motion along the x direction is equal to Ax. When you consider the fluid kinematics, when you write the fluid kinematics for steady flow, this is the Euler's equation for x direction, Euler's equation of motion along x direction, Euler's equation of motion along x. Okay, so that in fact what are this is a convective acceleration. This is a convective acceleration. I already told about the kinematics of fluid flow is the single most important chapter in FM. Why it is a single most important chapter is where you have to learn the types of accelerations also. In the kinematics of motion, you should know the acceleration has got two different kind of expressions. One is something is convective acceleration, other is a local acceleration. We should know the mathematical expression for them along x, y, and z directions. Okay, convective acceleration and a local acceleration. And again, in a cylindrical coordinate system, the tangential acceleration, there may be a tangential acceleration and normal acceleration. So in a cylindrical, actually see, when you are expressing the acceleration, two different coordinate systems we may consider, Cartesian and cylindrical. In the Cartesian system, ax, ay, az. In the cylindrical coordinate system, normal acceleration and tangential acceleration. But everything has got, in fact, has got again a local acceleration. Both the cylindrical coordinates and the Cartesian system will have the local acceleration component. But this local acceleration component will become 0 by default for a steady flow. For a steady flow, the local acceleration along any direction is 0. So, because the things will not change with respect to the time. So, that distinguishing we should know that. So, mind that, prepare a little bit exemplary notes for the kinematics of fluid flow, like in that order: types of fluid flow, velocity, potential, stream function, streamline definition, path line definition, continuity equation, types of accelerations, local acceleration, convective acceleration, normal acceleration and tangential acceleration. All these things, write them. And what is the flow net? What do you mean by flow net? And what do the difference between two streamlines? See, once you understand the streamline, we can say that the difference of the two stream functions psi1 minus psi2 will indicate the flow rate of the fluid passing between those two streamlines. Stream function is a mathematical equation indicating a streamline. Constant stream function line is nothing but a streamline. A streamline, I can also say this way: a streamline is that line for which the stream function value is constant at every point. If you take two streamlines, the difference between those two stream functions indicating those two streamlines will indicate the volume flow rate or the discharge of the fluid passing between those two streamlines. Such important points. The main idea of this last month preparation strategy is such important points we have to make a bullet points. You have to write it on like a précis manner. And entire fluid kinematics chapter we can reduce it to a simple one long page, one A4 size page. We can write all the points, the important salient points, and in the last minute we have to refer them, revise them. Very quickly you have to revise them 2 or 3 days before going to the exam, because things, last minute preparation also sometimes matters a lot, how quickly you revise. For that this 1 month preparation strategy I am giving, right? So, okay, coming to this fluid dynamics, going back to the fluid dynamics. So, we have discussed about the conservation of momentum, which is application of Navier-Stokes, application of the Newton's second law of motion. Conservation of momentum equations are two are there. One is Navier-Stokes equation of motion, another is Euler's equation of motion. Only difference is in the Navier-Stokes equation we have the viscous terms. In the Euler's equation of motion, viscous terms are not there, because while deriving the Euler's equation of motion, we have assumed that the fluid has got zero viscosity, inviscid fluid flow. So, non-viscous, zero viscous fluid flow, we have derived the Euler's equation of motion. If you consider the viscosity, you will get the Navier-Stokes equation of motion, right? Going to the another very important conservation rule in the fluid dynamics, which is called as the law of conservation of energy, or the law of conservation of energy, which is also called as the Bernoulli's theorem. The central concept of the fluid mechanics, Bernoulli's theorem, or the law of conservation of energy, P by W plus V square by 2G plus Z is equal to constant. The pressure is the sum of the pressure head, velocity head and the potential head or the datum head is constant. The total head of the flowing fluid remains constant between any 2 points in the fluid flow if there are no viscous effects considered. If there is no head loss due to friction, the total head of the flowing fluid remains constant between any 2 locations in the fluid flow. So, that point, that kind of things and its applications. Give a more focus for this area. Fluid kinematics and fluid dynamics, they play a major role. I said already, fluid mechanics, what is the weightage? 7 to 8 marks. Sometimes higher side 8, lower side 7, definitely I can say. So, the 1 mark may be asked in the fluid statics, maybe regarding the properties or regarding the buoyancy, regarding flotation or the manometry. And 2 or 3 marks may be asked in the fluid kinematics and dynamics put together. Okay. But in the entire FM, these 2 chapters are very important. Kinematics is important. The application of the kinematics you see in the dynamics also. But the main difference between the kinematics and dynamics is what? In the kinematics, we don't consider the forces. We simply describe the fluid flow. Whereas in the dynamics, we consider the various forces acting on the fluid element and try to write the Newton's second law of motion and form this conservation of energy. And by integrating that conservation of momentum, we get this conservation of energy. Integrating the Euler's equation of motion, which is a conservation of momentum, we get this conservation of energy, which is also called as the Bernoulli's theorem. Pressure head, velocity head and potential head, and everything has got the units of meter. Okay. You will find n number of questions asked in the previous gates on this Bernoulli's equation. So something like this you will ask. A nozzle is a nozzle is being, a jet is issued from a nozzle. To what height the stream jet may go, or it is impinging on certain hemispherical shell, what will be the force acting on that? Or water is falling from a tap, into a container, and at any instant of time, if m is the mass of the water in the container, what will be the reading shown by this weighing balance? This is some weighing balance. Questions may be asked like this. So to solve these questions, to solve any questions of fluid dynamics, we have to apply all the three conservation rules sometimes. And most of the occasions, two equations will solve. What are the three conservation rules I said? One is continuity equation, AB is equal to constant because the flow is incompressible. Second thing is the conservation of energy, P by W plus V square by 2G plus Z is equal to constant. Very interestingly and importantly, conservation of mass and conservation of energy are the scalar equations. They don't require any directions to be bothered. Okay. When you write the conservation of mass or the continuity equation, we don't look for the direction. Simply we write rho AV is equal to constant, AV is equal to constant. When you write the conservation of energy, we don't look for the direction. Simply we write sum of pressure head, velocity head and potential head is equal to constant. No bothering, no worry about the direction. But when you write the conservation of momentum, we have to consider the direction x, y and z, because conservation of momentum is an application of the Newton's second law of motion, which is a vector equation. It is not a scalar equation, whereas mass and energy are scalar quantities. Very easy to deal with the continuity equation and conservation of energy. But when you come to the momentum equation, we have to bother about the direction. So we have to make a small notes on these two chapters. I mean to say, give a more focus on this. You will definitely get 3 to 4 marks only on these two chapters. And coming to the another important chapter is incompressible flow through pipes. Incompressible flow through pipes. So again, we have to distinguish the flow into laminar turbulent flows by using this Reynolds number, most famous number. Only this is the number which can tell about whether the flow is laminar or turbulent, defined as the ratio between inertia force by viscous force. So whenever you talking about the laminar flow, again our main focus will be to calculate the head loss due to friction, HF. Whenever there is a flow happening, definitely the total head of the fluid keeps decreasing in the direction of the flow. Why? Because of the frictional resistance against the flow. As the flow taking place, there is a frictional resistance, and because of which fluid has to consume some of its energy and then maintain its flow. So whatever the work done by the fluid in overcoming that frictional resistance gets converted into heat. Of course, we cannot sense that heat because fluid swallows that, because fluid has got a high specific heat. We can't generally find the rise in temperature there. As the flow is happening, water is flowing in a pipe. Will there be any head loss again because of during its flow? Yes, definitely there will be, because there will be a frictional resistance. Why there is a frictional resistance? Maybe partly because of the viscosity, maybe because of the roughness of the pipe. So again, the frictional resistance may be caused by any of these two reasons or both. One is viscosity, because viscosity itself is a fluid friction. Fluid offers resistance against its own flow. So that is a viscous resistance, because of which head will be lost. Head means energy. When you talk about the Bernoulli's equation, what is this word head? Head and energy are same. Only units are different. Head in meters, energy is in joules. The energy of the flowing fluid per unit weight is called as the head. Energy of the flowing fluid per unit weight is called as the head of the fluid. So energy can be possessed in 3 different ways: pressure, kinetic and potential, or the Z. So this total sum of the energy in the direction of the flow, it keeps decreasing. slightly or greatly, based on what is the frictional resistance. The frictional resistance against the flow is owing to the viscosity of the fluid and also because of the roughness of the pipe. Between the pipe will have some roughness there, minutely small, but it has got some roughness. That is why smooth pipes will offer lesser frictional resistance as compared to the rough pipes. So, and which equations will important for this head loss due to friction? HF means head loss due to friction. So, what are the equations meant for that? This year we got the Huygens-Poiseuille equation, and whereas here we have the most prominent equation which is called as the Darcy-Weisbach equation, FLV square by 2GD. We all very familiar with this equation, FLV square by 2GD, where F is the friction factor. Actually, Darcy-Weisbach equation, though it is derived for the turbulent flow, many of the fluid flow problems it can be applied for the laminar flow. But this Huygens-Poiseuille equation, HF is equal to 32 mu V L by W d square. This equation is applicable only for the laminar flow. I repeat once again, Huygens-Poiseuille exclusively for the laminar flow. As long as the Reynolds number for the pipe flow it is less than 2000, it is laminar flow. It is greater than 4000, it is turbulent flow. Vd rho by mu. Reynolds number formula is Vd rho by mu, right? So, so we have to decide whether the flow is laminar or turbulent first. Reynolds number given, no problem. We can decide. If not given, calculate and decide. First make out whether the flow is laminar or turbulent, and then use the appropriate equation. And here for the laminar flow, particularly this friction factor will become 64 by Re for the laminar flow. That friction factor F, Darcy's friction factor it is called. F will become 64 by Re for the laminar flow. If you write the Darcy-Weisbach, if you equate the Darcy-Weisbach and Huygens-Poiseuille, you will get this. So, what is Moody's diagram? Friction factor, see, for the laminar flow, friction factor depends only on the Reynolds number, whereas for the turbulent flow, it not only depends on the Reynolds number, friction factor is a function of Reynolds number and as well as the relative roughness of the pipe. Epsilon by d is the relative roughness. Two parameters will decide the friction factor in turbulent flow. Friction factor in turbulent flow is a function of both Reynolds number and the relative roughness of the pipe. What do you mean by relative roughness? The epsilon is a small tiny projection of the rough pipe divided by the diameter. So, it is a dimensionless parameter. Basically, I want to say that all the three are dimensionless. Friction factor dimensionless, Reynolds number dimensionless, relative roughness is also dimensionless. And so, in the flow through pipes, another important thing is in the flow through pipes, what is the velocity distribution equation for the laminar flow? U is a function of R. What is its function? And for the shear stress, if you write the shear stress there, if you take the shear stress varies linearly. This is the shear stress, this is the velocity distribution. So, where the shear stress is maximum, where the shear stress is 0, you should know what are the velocity profile, what is the shear stress profile. Shear stress is also function of radius, where R is the radial coordinate measured from the axis of the pipe. So, these things we have to remember. The questions were very often asked. So, another important chapter. So, in that order of priority I am putting. First important chapter is kinematics of flow. Second thing is fluid dynamics. Third thing is incompressible flow through pipes. When you talk about the incompressible flow through pipes, we have to bother about the major losses, minor losses. Major loss is the head loss due to friction, and minor losses may be energy loss due to sudden enlargement, sudden contraction, etc., etc. But they are not that important. Minor losses we don't consider much. So, in the third important chapter is incompressible flow through pipes. Then comes another, particularly for the mechanical, that chapter which was recently introduced. That is, I think I still remember it is GATE 2020 or 19. At that time there was no change in the syllabus. For the last 4 years there was no change in the syllabus of the GATE mechanical. So, that chapter was introduced, I think it is GATE 2019 they have introduced, and that chapter is the compressible flow. It was not there. earlier compressible fluid flow is not there in the gates mechanical, but it was separate chapter one entity has been given. Now in gate 25 also it is there, because syllabus is no change in the syllabus for the last 4 or 5 years. So when you talk about the compressible flow, the first definition what we have to talk about is the Mach number. Velocity of the fluid divided by the velocity of the sound. If the Mach number, as I already said, when you call the flow as, when you identify the flow as compressible, if the Mach number of the flow crosses 0.3 equal or greater than 0.3, we can brand it as compressible. Or if the density changes of the fluid are more than 5% during the flow, you can brand it as compressible. So there are two ways you can tell. One way is if the density changes are of the fluid are greater than 5%, if the density becomes a function of pressure, okay. If density is constant, incompressible. If the density is a function of pressure, or if the density changes cannot be neglected, or if they are greater than 5%, you brand the flow as compressible. If the density changes are 1%, 2%, you can neglect that, you can treat the flow as incompressible. That means you can treat the flow as density as constant. So that is our Mach number. There are two ways there. Mach number greater than 0.3, compressible, less than 0.3, incompressible. And then, in fact, supersonic flow, if the Mach number is 1, sonic flow. If the Mach number is greater than 1, supersonic flow. If the Mach number is less than 1, subsonic flow. So we have to, that classification we should know. Subsonic, sonic, and supersonic. Hypersonic, that is rarely it will be given, because Mach number goes above 3. More than 3, that is hypersonic. We never bother about that. These three classifications we do. Mach number is 1 here. If it is less than 1, subsonic, greater than 1, supersonic. So particularly the questions were being asked repeatedly in a the flow of the compressible fluid in a convergent divergent nozzle. What do you mean by critical pressure? Here the critical conditions appear. In fact, this chapter is useful for the steam turbine nozzles also. Same concepts, but there in the steam turbines the flow is steam, here the fluid is steam, here the flow is air may be taken. So critical, what is the meaning of critical pressure? The conditions what we see at the throat, okay, for a maximum mass flow rate, when the flow rate is happening maximum, the things what you see, when the flow rate of the fluid in a convergent divergent nozzle is maximum, we can at that condition, the whatever the pressure, whatever the velocity, whatever the temperature, what you see at the throat of the convergent nozzle, divergent nozzle can be called as a critical conditions or a critical pressure. Its equation. What is a critical pressure equation? And you may have the shock, normal shock. This shock wave could happen only in the diverging portion of a convergent divergent nozzle. What is a shock? An abrupt deceleration of the fluid from the supersonic flow to the subsonic flow, during which the pressure abruptly increases and velocity greatly decreases. And of course, Mach number decreases, velocity decreases, pressure, temperature and density, all three will increase. So across this normal shock, here the Mach number is greater than 1. After the shock, the flow is happening like this. Before the shock, it is Mach number is greater than 1. After the shock, it is subsonic flow. So there is a highly localized irreversibilities. When I talk about irreversibilities, what is a parameter that comes into picture? Entropy. In the thermodynamic sense, I am talking. Because of this great irreversibilities during that normal shock wave, the entropy of the fluid will increase. So across the shock wave, you will have the increase of entropy, increase of pressure, increase of temperature, increase of density, but decrease of velocity. Great. Abruptly the flow becomes subsonic. So pressure will increase, temperature will increase, density will increase, velocity and Mach number will decrease. So that is what happens across the normal shock, and that could happen only in the diverging portion of a convergent divergent nozzle. So for the shock to occur, before the shock the flow must be supersonic. Okay. So give a more attention there. And what is the meaning of stagnation temperature, stagnation pressure, stagnation density? This whenever I given a naught, P naught, T naught, rho naught, they indicate the stagnation properties. The stagnation properties. You have to know the definitions of them. What is the meaning of difference between stagnation property and static property? And based on that, T naught by T is equal to 1 plus gamma minus 1 by 2 into m square. This relation also please remember. The link between stagnation temperature and static temperature. Okay, m is the Mach number, gamma you all know that thermodynamic sense, gamma is the Cp by Cv, that is the adiabatic index. So that there is this chapter give extra attention because it was a recently introduced chapter. Very often I am seeing the one question, definite one damn question they are asking in 23, 22, 24. Every year they are asking one question on this because it is something connected with the thermodynamics also. Compressible, actually as far as this chapter is concerned, thermodynamics and fluid mechanics becomes one and the same. So that is another important chapter in FM, and of course dimensional analysis is very simple chapter. Only we need to remember those all those numbers, that Reynolds number, Mach number already we have seen, Euler number, Fourier number, okay, Weber number. These numbers definitions we have to, formula not necessary, just remember the and Buckingham pi theorem. Buckingham pi theorem, and of course along that very more simpler theorem we have the Rayleigh theorem. Buckingham pi theorem and Rayleigh theorem. Okay, so these two this simple theorem. So that is all about the dimension analysis. And another small chapter only is there, that is the boundary layer, theory of boundary layer. Here also questions are coming very often, particularly the flow over a flat plate. One thing I would like to tell you that this chapter you know very clearly, if you know thoroughly this boundary layer theory, another subject, very important subject, heat transfer also will become easy. As far as the heat transfer and fluid mechanics are concerned, there are two important chapters in FM which you are essentially required to know to do the convection problems in heat transfer. What are those two? One is boundary layer theory here, another theory is the flow through pipes, incompressible flow through pipes. In FM, these two chapters, if you know thoroughly, one shot two birds like. If these two chapters, if you study thoroughly, that convection chapter in heat transfer subject also becomes very, very easy. You can solve any question there in the convection. Generally, most of the students feel tough that convection chapter. They leave, most of them, because in the colleges also teachers don't teach. They simply skip because they themselves don't know, may not be. Because that's what I observed in the colleges. But convection is an easy chapter if you know these two chapters in FM. What are those two chapters? Boundary layer theory and the flow through pipes. And why boundary layer theory is, this whenever there is a flow happening through over a flat plate, or for that matter any body, because of the viscous nature of the fluid, there is a thin region formed, very thin region. Actually, though I have drawn to this magnitude, in principle that the thickness of that boundary layer is very small. So there is a thin region formed around the body, inside which we see the velocity gradients. Velocity gradients appear. So we should know what is that. Velocity gradients, meaning that there is a variation of velocity in the y direction. Velocity keeps at any given x is measured from always the leading edge. X is the leading edge. Here x is this is the trailing edge. Here this is a free stream velocity. Velocity will be changing along the y direction. The last layer will be having 99% of the free stream velocity. So this region is called as the hydrodynamic boundary layer, whose thickness is indicated by delta, where delta is a function of x. It is the x coordinate, that is a y coordinate. So delta is this thickness of the hydrodynamic boundary layer is a function of x. So how to calculate that delta at any x? If that x gets doubled, how many times the delta will change? Here again laminar and turbulent. Here again the criteria will come, laminar and turbulent. But here that should be done by using the local Reynolds number, V infinity x rho by mu. So this we have to calculate the local Reynolds number and then decide the flow. Local Reynolds number where you have to calculate at the trailing gauge, and then decide whether the flow is laminar or turbulent. If this local Reynolds number is less than 5 lakhs, the entire flow is laminar. If it is greater than 5 lakhs, or 7 lakhs, if it is greater than 7 lakhs, the flow will be turbulent. Between 5 lakhs and 7 lakhs, there will be transition from laminar regime to the turbulent regime. So in the theory of boundary layer, we should know the definitions of the boundary layer. And what do you mean by boundary layer thickness? How does it vary with x? For laminar flow there is a separate function, for turbulent flow separate function. Delta is, I can say delta is directly proportional to the root x if the flow is laminar. Okay, not for the turbulent, I am talking about laminar. Delta is directly proportional to the square root of x, where x is the distance measured from the leading edge. For the laminar flow, if here the laminar flow means Rex is lesser than 5 lakhs, local Reynolds number at x is equal to L. Okay. So, and of course drag force. Very often the questions are asked on the drag force. How to calculate the drag force? What is the coefficient of drag? Or drag coefficient or coefficient of drag all mean the same. CD they call coefficient of drag or drag coefficient, which is a non-dimensional parameter. How to calculate the drag coefficient? How to calculate the drag force exerted by the fluid on the plate. So that is another important thing, drag force and drag coefficient. CD, coefficient of drag or coefficient of drag coefficient, frictional drag coefficient all mean the same. It is a dimensionless term. Drag, how to calculate the drag force and how to calculate the drag coefficient. That particular analysis you have to, small chapter only, not a big chapter. Dimension analysis and boundary theory is small chapters, not a big. Big chapters are kinematics of fluid flow and dynamics of fluid flow and incompressible flow through pipes. They are the three big chapters. But if you prepare those three, flow through pipes, dynamics of fluid flow, and of course when I talk about dynamics of fluid flow, I would like to tell you that applications of the Bernoulli's equation in the Venturi meter, in the pitot tube, particularly those two, Venturi meter and pitot tube. Try to just give a look at the orifice meter also, that was not asked frequently, but mainly two things were asked. Venturi meter meant for the measuring discharge, second thing is the pitot tube meant for measuring the velocity. So focus on that particular two applications of the Bernoulli's equation in the flow measurement, velocity measurement and discharge or flow rate measurement. Okay. And how to write what is in fact how to get, what do you get the Venturi head, from the Venturi head how to calculate the flow rate formula. No, you know that this very famous formula, discharge formula for the Venturi meter, Q is equal to coefficient of discharge A1 A2 root 2 GH by square root of A1 square minus A2 square, where A1 is the inlet area and A2 is the throat area. And a U-tube manometer is connected here. A U-tube manometer is connected between the inlet and the throat, and you will be, by just measuring the difference in manometric level differences in the left limb and right limb, you would be able to calculate H. That H is called as the Venturi head, x into square root x into Sm by S minus 1, where Sm is the specific gravity of the manometric fluid, S is the specific gravity of the flowing fluid, X is the, what is X? Difference in mercury levels. A1 is the inlet area and A2 is the throat area. Okay. So of course this formula for the discharge in the Venturi meter is obtained only by writing the continuity equation and Bernoulli's equation. I already said any problem of FM can be solved only by these three conservation rules. Conservation of mass, continuity equation, conservation of energy, that is Bernoulli's equation, and conservation of momentum. When you talk about the conservation of momentum, forces we have to deal, forces over pipe bends also. Impact of jets and forces over pipe bends, that is also important case. A jet is issuing from a nozzle and for a moving plate, a jet is issuing and striking. A jet is striking. How to calculate the force exerted by the jet on the moving plate? Okay, this is a plate is moving. Or sometimes plate may be stationary. Sometimes a moving jet can be impinging over a vane. That is also the impact of jets. That is application of the conservation of momentum. Application of the conservation of energy, Bernoulli's equation, that is Bernoulli's equation you see in the Venturi and pitot tube. Whereas application of the conservation of momentum you see in the forces in bends, forces exerted by fluid over a pipe bend. Okay, give the more important area. This is because conservation of momentum is slightly you have to give a extra care because it involves direction. Conservation of momentum is an application of the Newton's second law of motion, which is a vector equation, so you have to bother about the direction. Continuity and Bernoulli's equation, we don't have no worries about the direction because they are scalar equations. So we have to write the carefully that how to calculate the force exerted by the jet, net force exerted by the jet. A jet, water is issuing like this and the water is leaving like this. What is the force exerted by the water on this pipe bend, which is observed in the plan view, top view. Okay. So these two are the applications of the conservation of momentum. So once you know this conservation of momentum application called impact of jets, you should be able to switch over into the another important chapter called as a hydraulic turbines. Only we have three turbines, Pelton wheel, Kaplan and Francis, but most of the questions will be asked in the Pelton wheel. Okay. Most of the majority of the questions. Just try to remember that Euler's turbine equation, which is a generalized equation for any turbo machine, and how to apply it for the Pelton wheel. And just when you talk about the hydraulic turbines, we should know what classification of the turbines, we should know what is the specific speed. And on entire hydraulic turbines, we can write it on a Prezi note or a one page. We have to classification of the turbines based on the head, based on the specific speed, based on the type of flow, etc. And then velocity triangles, how to construct the velocity triangles, particularly for the Pelton wheel. You don't have to study Kaplan and Francis in detail. Okay, but recently, of late, no questions were asked in the hydraulic turbine, but we can't take risk. Just give a look at the hydraulic turbines also, how to draw the velocity triangle, mainly for the Pelton wheel. For that, you should know the application of the impact of jets. That application from the both are application of the conservation of linear momentum, or which is all, what is the other name is impulse momentum equation. It is famously known as impulse momentum equation. Impulse momentum theorem they call, or impulse momentum equation they call, all mean the same. Impulse momentum equation, that how to write for these two cases, just try to learn that. So this is all about FM. So finally I would like to say regarding FM, took fluid kinematics, fluid dynamics and incompressible flow through pipes is easy chapter, because just we have a specified equations are there, Hagen-Poiseuille, Darcy-Weisbach, friction factor, and not a big chapter, that is incompressible flow through pipes. The entire chapter can be written present in a half page. And then coming to the applications of the Bernoulli, applications of the conservation of linear momentum. And dimension analysis I already said, only learn about those 5 numbers. Okay, just learn about the dimensions there. Which number will talk about which force. For example, Weber number is there. Weber number is important, particularly surface tension force. Or Fourier number is there. Okay, Fourier number is pertaining to the gravity force. Euler number is there, it is pertaining to the pressure force. Reynolds number is pertaining to the viscous force. Mach number, it is pertaining to the elastic force or the compressibility force. When you talk about the Mach number, immediately the compressibility effects come into picture. What do you mean by compressibility effects? The density of the fluid is liable to change, likely to change. If it is an incompressible flow, density will never change. Density is a constant. Okay. So this is all about FM. Let me go to the next another important chapter called heat transfer. Of late, particularly in the since GATE 2022, particularly observed 22. I think in GATE 22 he has asked 13 marks. I think 12 to 13 marks. Highest in that GATE. Tough questions. All questions were tough in this. In this heat transfer, still say GATE 2022 he has asked I think 12 to 13 marks. In GATE 23 has asked 24. In all these for the last 3 years, the weightage of the heat transfer is showing more. I don't know the reason, but is showing more. Usually the average weightage will be around 8 marks. But 29, 23, 24 also giving a weightage is 9 marks or 10 marks it is going. But average weightage is I can say 8 marks in gate. 8 marks is a very good weightage in heat transfer. 8 to 9 marks sometimes it is touching. Many gate papers. It is highly mathematical subject and easy also, because we have to broadly divide the syllabus into 3 chapters, conduction, 4 chapters, conduction, convection, heat radiation and heat exchangers. Conduction, convection, radiation and heat. This is the easiest chapter. So you don't don't miss this chapter, easiest. So because why it is easiest is only 2 methods are there, only 2 methods. When you prepare a short notes, only 2 methods. What are the 2 methods? LMTD method and effectiveness NTU method. Any problem of heat exchangers must be solved by one of these 2 methods. LMTD method is meant for finding the area or the design of heat exchanger. This method is meant for the performance of heat exchanger. Okay, effectiveness NTU method is meant for performance, and this LMTD is meant for finding the area of the heat exchanger. So first finish that chapter in the conduction, in the heat exchangers, because you may get one question in that, because in that year 2022 he has distributed 13 marks, he has distributed all the chapters. Generally people see convection as the toughest. Actually it is very easy. I already given the clue, provided you know the boundary layer theory in FM and also the flow through pipes in FM. If those 2 chapters are thorough, this convection chapter also becomes easy. Conduction is a bigger chapter. Conduction is a big chapter, conduction, because it has got so many cases: composite wall, composite cylinder, okay, composite cylinder and critical radius. In the conduction chapter, if any questions are asked, mostly I will give the chances for the critical radius of insulation, number 1. Number 2, unsteady state conduction, unsteady Biot number, transient, unsteady state conduction or transient, particularly definition of the Biot number, and of course Fourier number. Biot number and only these 2 numbers will come in the FM, come in the conduction chapter, Biot number and Fourier number. Okay, particular that lumped heat analysis, that is unsteady state lumped heat analysis. That particular chapter very often they ask, when this lumped heat analysis is applicable, what is the criteria to apply that lumped heat analysis? What do you mean by lumped heat analysis? We assume that the temperature of the body changes only with the time. There are no internal temperature gradients, internal temperature variations. The whole body, the entire body is supposed to be at one temperature. The core of the body and the periphery of the body. Core of the body and the periphery of the body, everywhere the temperatures are same, but the temperature of the body keeps changing with time. Such thing is called as the lumped heat analysis, where the Biot number is the criteria. But critical radius of insulation is another example, and fins. Fins is also, when you talk about the fins, only 2 parameters we have to remember: efficiency of the fin and effectiveness of the fin. Efficiency of the fin, we already know the formula, tan HML by ML, okay, and where M is the root of HP by Ka. In fact, efficiency, this is the effectiveness of the fin, square root of HA by Kp. Effective, 2 definitions are different. Effectiveness and efficiency are different. So remember, by default, always consider the insulated tip case. When you talk about the fin analysis, you always consider the insulated tip case by default. You assume that the tip of the fin is insulated and then try to solve the problem, unless he specifically mentions a very long fin. Actually in the fins you got only 2 cases. 3 are there, but 3rd case is unimportant. 2 you can remember. One is very long fin case, infinitely long. Second thing is finite length, but the tip is insulated. So you remember those 2 cases. To calculate, only 2 things will be there: how to calculate the heat transfer rate, how to calculate the temperature distribution inside the fin. So in the conduction chapter, one is composite wall case, like composite cylinder case, and recently very often the questions are asked in the heat generation. This question is very commonly coming. Heat generation in conduction chapter, particularly in conduction chapter, heat generation in slabs or cylinders. Spheres they are never asked, but cylinders also they may ask. When they talk about the heat generation, you get the Q dot. This will see heat generation. So when a slab is generating heat uniformly, this temperature may be given, this temperature may be given, the and we have to write the equation dou square T by dou x square by assuming plus Q dot by assuming that one dimensional conduction steady state 1 by alpha dou 2 by dou tau, and this alpha is the K by rho Cp, which is also called as the thermal diffusivity, a thermophysical property of the material. So this is for unsteady state, the temperatures won't change with time. So in fact this tau is the time parameter. So this will become 0. Alpha is the thermal diffusivity, and we have to integrate this equation. It is a second order equation. We get two constants of integration. It is a second order equation. Q dot is the rate of heat generation. Heat is being generated uniformly throughout the slab. So K is the thermal conductivity of the material. So if you integrate this equation, we get the two constants of integration. Those two constants of integration will be obtained from the two given boundary conditions, T1 and T2. Because this x may be considered as a coordinate, because x may be 0 here, x is equal to L, because some books will give the x is considered at the mid plane. Look at my videos there. I already given the very elaborative videos regarding this heat transfer. Go through my videos which are given in the heat transfer. Those students who have joined our coaching program already have taken the videos there, and these cases have done it very elaboratively. And there is a heat generation in a slab and also the heat generation in a cylinder. When heat is generated, generally they may ask what will be the temperature varies parabolically. Here also the temperature varies parabolically. If T1 is greater than T2, the peak temperature we will see in the left half. If the T2 is greater than T1, if this T max we will see in the right half of this slab. Okay, but this is definitely a parabolic temperature distribution. By integrating this differential equation, we get the parabolical temperature distribution. Temperature is a function of x. Okay, what kind of function? It is a parabolic function. So the questions may be asked like this in this particular, because in every GATE exam is asking these cases, heat generation case. What is the question they may ask? What is the maximum temperature? How much is the maximum temperature in the body? Number one. And where do you see that? Where will you see that inside the slab? At what location of x you see that maximum temperature? So these give more attention to this case. And this heat generation inside a heat generation in cylinder. This is another heat generation in cylinder. Q dot, is that right? So here parabolic temperature, you will definitely see the maximum temperature at the axis, right? So definitely there will be a convection happening from the center of the rod. So without this convection, we cannot maintain the steady state. Whenever there is a heat generation, by default you assume a steady state. What do you mean by steady state conduction? The temperature at a particular location will not change with respect to the time. The temperature at a particular location will not change with respect to the time. Almost throughout the subject, we always assume the steady state, except in that particular topic called unsteady state conduction or lumped heat analysis, where we have defined Biot number and Fourier number. Biot number and Fourier number you will see in that Heisler charts. See, you should just have a look at the Heisler chart. In the Heisler chart, you will see the Biot number. Okay, in the Heisler chart, particularly in the previous conduction chapter when I was discussing, Biot number and Fourier number, you will see both of them in the Heisler chart. Heisler chart is required if the lumped heat analysis is not applicable. If the Byte number calculated greater than 0.1, lumped heat analysis is not applicable. Then how to solve the problem? By using this Hausler chart. In that chart, you will see both the numbers, Fourier number and Byte number. Learn those definitions. Byte number is defined as internal conductive resistance by external convective resistance, and Fourier number is a dimensionless time, they call dimensionless time, alpha T by R square, its formula. Okay. Thermal conductivity by thermal storage ability, that is called as the Fourier number. Okay. Thermal conduction, heat conduction rate divided by heat storage rate, that is called as the Fourier number. Internal conductive resistance divided by external convective resistance is the Byte number. So, how to read that, just have a look at the Hausler chart. How does it look at? And questions he has asked once in GATE 2008, question on Hausler chart. Very, very important question, GATE 2008 conducted by IISc Bangalore. So, heat generation, where you see this generally maximum temperature is indicated by T naught, how to calculate the surface temperature, and how to calculate the maximum temperature. Here by default maximum temperature will happen at the axis. So, this is all about the conduction chapter. So, in the conduction chapter, give more attention to the heat generation cases, and then the critical radius of insulation, K by H formula, and also the unsteady state transient heat conduction or lumped heat analysis where is applicable Byte number, etc., and also the conduction through slabs. When you talk about the conduction through slabs, generally whenever you talk about a conduction through slabs, you may be required to calculate which thermal conductivity is more. For example, the question may be asked like this. By looking at this formula, if the heat conduction is happening like this in a composite slab, K1 is more or K2 is more, means just by looking at the profiles I can say K1 is more, K1 is greater than K2. Fourier law, see, before starting chapter heat transfer, learn thoroughly about these three laws: Fourier law of conduction, Newton's law of cooling meant for the convection, and the Stefan-Boltzmann law of radiation. Of course, there are some other subsidiary laws also there in the radiation. So, these three laws you will learn it thoroughly before starting the preparation of the heat transfer subject. Coming to this composite slab case, the most likely thing that may be asked is, you will be given a composite slab with two different materials attached together having two different conductivities. You should understand how to construct the thermal circuit. Sometimes there will be definitely a given convection will be there, convection. We have to find out what is the resistances. Convection resistance here, 1 upon H1A, here the 1 upon H2A, convection resistance here. So, what is the conduction resistance formula? B by Ka, B1 by K1A, B2 by K2A. So, we should know how to construct the thermal circuit. Okay. If you are not able to construct a thermal circuit wisely, you cannot do the problem on the composite slab cases and as well as the composite cylindrical cases. In the very first chapter of conduction, which is the biggest chapter of heat transfer, in GATE point of view, just to try to learn how to construct the thermal circuit. So, when you construct the thermal circuit, you must be very thoroughly and understand what are the terminals. Supposing if this is a composite slab exposed to the convection conditions on both sides, we have the four resistances if this is the direction of the heat flow. Convection resistance here 1 upon H1A, where A is the area of the slab, B1 by K1A, this is B2 by K2A, this is 1 upon H2A. So, this rate of heat transfer can be calculated by connecting all these resistances which are in series. It is a series circuit because first convection, then conduction and again convection. So, all the resistances are connected in series, mostly series only. Only once in GATE 2004 I guess he has asked the slabs connected in parallel, something like this. I will just show you, but that is a rare case, but still I can say this is a slab, two different materials, this is A, B and C. Then the thermal circuit will be like this. Resistances must be connected in parallel because heat conduction happens simultaneously through B and C. This is the resistance of B, this is the resistance of 3, this is the resistance of A. So like this things may be given, but this is a rare case, but most of the cases you will give the series case, okay. And we should be able to identify the, if this is Tg and this is T infinity, this is Tg and this is T infinity, heat transfer happens like this. This is a convection resistance, this is a conduction, this is again conduction resistance, this is convection resistance. So any temperature they may ask the interface temperature, they may ask this slab temperature, or they may give this and this, they may ask you to calculate the right side. So we should be able to thoroughly calculate, you should be able to calculate either the temperatures at any location or the heat transfer rate, okay. So this is a very easy also, not at all a difficult. You just only thing is there are only two kinds of resistances are there, B by Ka for the slab, convection 1 upon Ha. If it is a cylindrical case, say for example, if it is a radial conduction case, the heat transfer is happening radially. Heat conduction happens radially. Under such case, the formula for the resistance will be, if this is R2 R1, ln R2 R1 by 2 pi KL. This is the resistance for the conduction resistance for the hollow cylinder, okay, radial conduction case. Heat transfer happens radially. Just so, when you are preparing a short notes for the conduction chapter, first take case after case. See, in the heat transfer conduction chapter, you should be able to distinguish one case from the other. Sometimes there will be a heat generation, sometimes there will not be heat generation, sometimes things will be steady, sometimes it will be unsteady, sometimes one dimensional, but two dimensional case they are never given. I think only once he has given, that is gate 2008 I guess, only multi-dimensional has given. But in the last 25 years of gate, except that gate 2008, I have never seen conduction problem given in a two-dimensional, okay. All are one-dimensional. Most of the case steady cases, but unsteady state is also there. Transient conduction case where the lumped heat analysis is unsteady state. So that may be given very often. Except that all other cases are steady conduction, and sometimes they may ask the variable conductivity. Okay, variable thermal conductivity. But I think gate 22 has asked the variable thermal conductivity, but only once or twice only it has come. Majority cases we assume that K is a constant thermal conductivity. And particularly you should have a rough idea about which material has got better conductor than the other. Supposing if you are given iron, you are given a copper, you are given a aluminum, you are given a wood, you are given a air. Which is the least conductor? Air. All gases have got very low thermal conductivity. Air conductivity is just 0.026 watt per meter Kelvin, very low. Best conductors are metals. Among them, copper is the highest, silver and copper have got the highest. Lowest in the generally metals will be steels will be having around 30. So we should have a rough 30 watt per meter Kelvin. I am talking about K, units are watt per meter Kelvin. We should have a rough idea about which material is better conductor, which material is a bad conductor. All the wood insulators have got poor conductors, glass wool, rock wool, etc. They are all poor conductors, right? So in the conduction chapter, most important things are heat generation, composite slab cases, how to get the temperatures, and the transient conduction, heat conduction, and critical radius. Prepare the short notes in that important things, and try to distinguish from case to case. Fins also given, but not many times. Just when the fins, when you talk about the fins, only remember that insulated tip case, how to calculate the heat transfer rate, what is the formula for the temperature distribution inside the fin. Temperature is a function of the x. If the fin is there, just consider that insulated tip case, assume that the tip is insulated, and temperature is a function of x, and terminologies, the base temperature, m is equal to root of Hp by Ka, where A is the profile area, P is the perimeter, K is the thermal conductivity, H is the convection coefficient. So how the temperature changes with respect to the x? That temperature is a function of x. So this is the base temperature. So you have to learn about the terminologies. Once you remember what are the terminologies, remembering the formula is not a big thing. you should understand first any fin problem try to calculate that m units are per meter, root of hp by ka. A is the not the surface area, A is the profile area or the cross sectional area, K is the thermal conductivity of the material, P is the perimeter, H is the convection coefficient given in watt per meter square Kelvin, right. So this is all about the conduction. Coming to the heat exchangers have already think there. Coming to the convection there. Generally people think convection is a tough, but actually it is easy. Only thing is we should know the dimensionless numbers, how to calculate. Important numbers are Reynolds number, Nusselt number, Prandtl number. In the force, actually first distinguishing we have to do forced convection or a free convection. Just decide first. If you see a velocity or a flow rate forced, if there is no velocity or and there is no nothing velocity given, it is a free or a natural convection. But natural convection in the last I can say 25 or 30 years, natural convection questions were given 2 or 3, maximum 2 or 3 times. 2 times I guess. Once he has asked the Grashof number, in the free convection you will get the Grashof number. Whereas in the forced convection you see the Reynolds number. Reynolds number you will not see here, Grashof number you will not see there. But in both the things common will be Nusselt number and Prandtl number. Prandtl number is the most important number asked in the convection questions. Kinematic viscosity divided by thermal diffusivity, that is the formula for the Prandtl number, mu Cp by K. It is a property, thermophysical property of the material. Prandtl number is the thermophysical property of the material. No other number is a thermophysical property. All other numbers, none of them is a property. Only Prandtl number is a property because it is the number which connects HBl thickness and TBl thickness. HBl thickness delta and TBl thickness delta T. Thermal boundary layer thickness delta T and hydrodynamic boundary layer thickness delta, both are linked by this Prandtl number. If we just know the Prandtl number, you can immediately tell whether HBl is thicker or the TBl is thicker, whether delta is more or delta T is more. We can immediately declare just by seeing the Prandtl number value. Prandtl number for the air is 0.7, Prandtl number for the water is around 2 to 6. It varies with temperature. So just give me the Prandtl number, I can immediately tell you. If the Prandtl number is greater than 1, delta will be greater than delta T. If the Prandtl number is less than 1, delta T will be greater than delta. If the Prandtl number is 1, near 1, delta will be almost equal to the delta T. So these questions on Prandtl number are asked n number of times in GATE. So try to learn the definition, and by seeing the Prandtl number you must be able to judge which boundary layer is relatively thicker than the other. So that particular point you have to keep in remember. And even the forced convection, Nusselt number is a function of Reynolds number comma Prandtl number. Here in the free convection, Nusselt number is a function of the product of Grashof number and Prandtl number, which is also called as the Rayleigh number. The product of Grashof number and Prandtl number is also called as a Rayleigh number. Okay. Nusselt number in the forced convection only Nusselt, Reynolds and Prandtl. Nusselt number definition is Hd by K. K is the thermal conductivity and Prandtl number is mu Cp by K. We know the Reynolds number definition also, right? Okay. And when after seeing the problem, forced or free you decide. Mostly forced it will be, because free convection cases 2 or 3 times only. In the forced convection, whether it is internal flow or external flow, decide first. Internal flow means flow through pipes, like a duct, a pipe flow or a duct. If it is an external flow means they will ask obviously flow over a flat plate. Okay. And then after calculating after identifying internal flow or external flow, first calculate Reynolds number. And from that you decide the flow as laminar or turbulent. That is the first thing. For dealing the convection problems, first decide the flow as laminar or turbulent, and then pick up the formula, this relation. Nusselt number is, what is the formula? Hd by K. After all, our main objective is to calculate the H. Therefore, so first calculate the Reynolds number, decide the flow as laminar or turbulent, and pick up that formula. And then from that try to calculate the H. Once you calculate the H, Q is equal to HA delta T. Newton's law of cooling. Once you calculate H, immediately we can get the heat transfer rate, HA delta T. A is the area of contact or area of heat transfer. Convection area is always a contact area between the body and the fluid. Okay, delta T is the temperature difference. Right. Now, this is actually convection chapter is quite easy. But when you talk about these definitions, all numbers we should know. The Grashof number, he has asked the definition. I think once or twice he has asked. What is the definition? Buoyancy force divided by viscous force. That is a Grashof number definition. Okay. G beta delta T. G beta delta T L cube by nu square. This is the definition of the formula for the Grashof number, buoyancy force by viscous force. Right. So this is all about the convection, and then coming to the radiation. The main thing, radiation, important things where you have to give more focus is definitions. All definitions: total emissive power, emissivity, grey body, black body definition, grey body definition, monochromatic emissivity and monochromatic emissive power, E lambda, EB lambda. Okay, everything we have to thoroughly understand. And opaque body, what do you mean by opaque body? Black body, opaque body, all these definitions we have to learn in the radiation chapter. Easy only, there is not a big thing. What do you define the total hemispherical emissive power? It is the amount of the radiation energy emitted from the surface of a body in all possible hemispherical directions and all wavelengths. Because radiation happens over a certain bandwidth of wavelengths. Radiation emission will happen over a certain bandwidth of emission on the electromagnetic spectrum between 0.1 microns to the 100 microns. So it is spread over that electromagnetic spectrum. So what is the total energy emitted, integrated for all the wavelength ranges in the electromagnetic spectrum, integrated in all the directions. So energy may be emitted not only in one particular direction, it is emitted in all the possible hemispherical directions. We have to add up every energy emitted in all the directions. What you get is the total hemispherical emissive power, having the units of watt per meter square. Then what is monochromatic emissive power? Energy emitted at a particular wavelength. Energy emitted at a particular wavelength in all hemispherical directions is called as the monochromatic. This is epsilon lambda is the monochromatic emissive power of the non-black body to the monochromatic emissive power of the black body at the same wavelength, at the same temperature also. So whereas epsilon is equal to E by EB. So these definitions we have to thoroughly understand, and if the epsilon lambda is constant, is independent of the wavelength, it is called as a grey body. Black body is a perfect absorber and ideal emitter. Black body absorbs all the radiation incident upon that. At the same time, as compared to all other non-black bodies, black body emits more radiation. If 10 bodies are there, all are at the same temperature, black body emits more as compared to the all other remaining 9 non-black bodies. So that definitions of black body, and more importantly loss of thermal radiation. Actually there are 5 laws are there, out of which 4 are very important. Kirchhoff's law, absorptivity is emissivity, alpha is epsilon. A perfect absorber is a ideal emitter. A good absorber is a good emitter. That is Kirchhoff's law, valid for both non-black and black. For black body both are 1, absorptivity is 1 and emissivity is 1. And please remember these 4 definitions also: absorptivity, reflectivity, transmissivity. These definitions also you should know. Alpha is absorptivity, rho is reflectivity, and tau is transmissivity. If the tau is 0, such body is called as the opaque body. Fine. And then Wien's displacement law, Stefan-Boltzmann law. Okay, Stefan-Boltzmann law, Wien's displacement law, and Planck's law. Planck's law of electromagnetic thermal radiation. Planck's law of thermal radiation. And one more law is there, Lambert's cosine law, that is not much important, that is regarding the diffuse surface. Lambert's cosine law, that is pertaining to the diffuse surface. Okay, a diffuse surface is the one whose monochromatic intensity of radiation is same along all the directions. If the intensity of radiation is same along all the directions, such body is called as a diffuse surface. I repeat once again, if the intensity of radiation is same along all the directions, such surface is called as a diffuse surface. If the monochromatic emissivity epsilon lambda is constant independent of wavelength, it is called as a grey body. When you talk about when you do the radiation problems, we assume that the surfaces are diffuse and grey. What do you mean by grey body? Monochromatic emissivity is independent of the wavelength. What is a diffuse surface? Intensity of radiation, the amount of energy radiated in a particular direction is called as the intensity of radiation. If that is same along all the directions, such body is called as a diffuse surface. Black body by default is a diffuse surface. Black body has three characters: perfect absorber, ideal emitter, third in nature is diffusive in nature. Okay. So these are the important things, definitions you should know. And then the very commonly asked question in radiation is shape factor. Shape factor and reciprocity theorem, reciprocal relation, reciprocity theorem pertaining to the shape factor. A1 F12 is equal to A2 F21. You know this, how to make use of the reciprocity theorem in solving the shape factor problems. Every gate exam, usually when you see one question, one mark question, you will see the regarding the shape factor. It has got other names also. View factor they call, configuration factor, all mean the same. So this is pertaining to the shape factor problems there. We ought to geometry. Generally they will ask one circular surface is bound by hemispherical shell. A circular surface is bound by hemispherical shell, and you will call this as one. And when you do the shape factor problems, be careful about which number is which surface. Sometimes by to cheating you may to deceive you will keep one here, to keep there, to confuse you. So the relation will change. Okay, that value will change. So when you are using this reciprocity relation, what is 1, what is 2? We have to have a clear idea, and what is the shape of that surface, what is the area of that surface, you should know. Okay. Shape factor give more important there. Then comes to the important cases of the radiation. To infinitely large, very often asked case this is. To infinitely large planes, the net radiation heat transfer, what is that? T1 power 4 minus T to the power of 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So this kind of emissivities are given, and temperatures are given. We should be able to calculate the net radiation heat exchange. In fact, this problem was quite often asked in many gate exams. When are two diffusively grey surfaces, large planes, radiation heat exchange between two large planes, infinitely large planes, diffuse surfaces, grey surfaces, temperatures are given. We need to calculate the net radiation heat transfer, T1 being greater than the T2. This is a very common thing. Another thing you may ask, between two infinitely long concentric cylindrical surfaces. This is another case. Q122 net radiation heat transfer will be sigma T1 power 4 minus T to the power of 4 into A1 divided by 1 by epsilon 1 plus A1 by epsilon 2 into 1 by epsilon 2 minus 1. So see, the two important cases. One is infinitely large planes, infinitely long concentric cylindrical surfaces. And many gate exams twice is asked, what is the shape factor? Say for example, two infinitely long concentric cylindrical surfaces are there. This is 1, this is 2. You will ask something like F2, what is F2? What is the self-shape factor? Only a concave surface will have a self-shape factor. So how to make use of the reciprocity theorem? and the summation rule. Actually, when you talk about the shape factor, whenever a question is asked in the radiation, one must be thorough, very thorough about the radiation shape factor. Okay, in that radiation shape factor, main theorem is reciprocity theorem. A1 F12 is equal to A2 F21. Okay, in general, AM Fmn is equal to AN Fnm, I can say. Second thing is the summation rule. In an enclosure, if there are n number of surfaces are there, F11 plus F12 plus F13 plus etc. F1n is equal to 1. The sum of all these shape factors is equal to 1. That is another important rule called as a summation rule. Here, say for example, there are only two surfaces are there, F11 plus F12 is equal to 1, F21 plus F22 is equal to 1, like this. In an enclosure, if there are only two surfaces, this surface is 1 and this surface is 2, F11 plus F12 is 1, F21 plus F22 is equal to 1. So, how to make use of this summation rule along with the reciprocity? That will be sufficient to solve most of the problems of radiation. Actually, there is one more important rule is there, that is called as a principle of superposition. That is also called as the superposition rule, superposition principle. The sum of this shape factor is equal to a given shape factor is equal to sum of its parts. Okay, generally it is done like this. This is 1, this is 2, this is 3, whole thing is 4. F14 is F12 plus F13. F14 is 2, 4 is the sum of 2 and 3. 4 is the sum of 2 and 3. If 4 is divided into two parts, F12 plus F13 is equal to F14. That is called as the principle of superposition. With these three rules and shape factor definition, most of the problems of radiation problems can be solved. Okay. So, as far as the radiation chapter is concerned, remember the laws, remember the basic definitions, try to focus more on the shape factor, more on the most important topic is shape factor, and how to calculate the net radiation heat exchange. In GATE 20 or 19 in those areas, in those years, he was asking some very typical problems. For that, we have to know how to construct the radiation networks. Supposing if this is one surface, this is two surface, this is surroundings, this is surroundings. You will give that you will give the shape factor there, you will give the shape factor between one of them, F12 will be given, you will be given the dimensions. What is the net heat transfer between one and the surroundings? This is one of the gate question he has asked. Or in another gate he has asked a rectangular duct, very long rectangular duct, very long, infinitely long rectangular duct. Then what he is asked, what is the net radiation heat transfer or total radiation heat loss from the surface one. So, to understand that one, this such kind of a problems must be solved by radiation networks, where we define two kinds of resistances, surface resistance and space resistance. To construct the radiation networks, we should understand first what is a surface resistance. This is the surface resistance, space resistance is. Space resistance will exist between any two surfaces. Surface resistance will exist over every surface. For the black body, surface resistance is 0 because for the black body emissivity is 1. So, we have to wisely construct the surface resistance, and then you should widely understand the radiation networks. For example, if you take this one, these two surface and surroundings, you name it as 3, each one has got one surface resistance. Between any two, there will be a space resistance. When you define the space resistance, that will be existing between two surfaces. When you define the surface resistance, that will be existing over a surface. So, here if you take this as 1, this as 2 and this as 3, each surface has got one surface resistance. Between any two, between them there is one space resistance, between them there is one space resistance, between these two there is another space resistance. Okay. So, radiation networks must be thoroughly understood to solve such kind of a problems. And the definition, but before going to radiation networks, you should know the two definitions called as irradiation G and radiosity J. Irradiation G and radiosity J. Prepare a short notes actually, because so most of the questions in radiation, they will be asked about shape factor, and also some questions were asked in the regarding the radiation networks. Both the questions were asked in two different gate question papers, this geometry and this geometry. You may refer to the previous problems. One important strategy of planning for the gate is go to the recent year gate papers for the last 10 years. Try to solve those problems on your own. Definitely that will help you a lot to manage the time while doing the problems, because see, in the gate it is all about time management. 3 hours 100 questions, 3 hours 100 questions, out of which 13 marks mathematics, 15 marks aptitude, which are relatively easy, but 72 marks core engineering. See which question we have to pick up, how quickly, how rapidly you are going into the inside of the problem. The moment you read the problem, you have to catch up the core concept pertaining to the solution. You have to catch up that core concept, immediately, rapidly apply that concept and then quickly get the answer, because it's all about time management. And also there is a danger of negative marking, particularly in the multiple choice. Okay, there is a negative marking is there, not in the NDT type, but in the multiple choice there is a negative marking. So there, if you wrongly select any wrong answer, that already one question will take away the negative marking. So the time management, how quickly you respond, how quickly you will go into the core essence of the problem solution. And then finally, after getting the answer, we have to type it there. And sometimes while typing, we have to look at the answers correctly. The answers, you got a degree Celsius answer, but he has asked the answer in Kelvin. You have put up the Celsius, that is correct answer only, but he has asked the Kelvin units. You have to add the 273 and put that. So which units he is asking, either it is answer is in watts, answer is in kilowatts, or whether it is degree Celsius or a degree Kelvin, all that we have to, whether it is a kilonewtons answer or a newtons. So that is all about this radiation here, and that in fact that is the regarding the heat transfer subject. Heat exchangers is a very easiest chapter. In the heat exchangers, easiest, only two methods, LMTD and effectiveness NTU method. And special cases you have to remember, particularly what if m dot h CPH is equal to m dot c CPC, it is called as a balanced counterflow heat exchanger. In counterflow heat exchanger, most of the cases you will give this case. I don't say that in every heat exchanger it happens, particularly in a counterflow heat exchanger, if the capacity rates are equal on hot side and cold side, it is called as a balanced counterflow heat exchanger. This, in such case, there is certain special cases will arise, where if it is a balanced counterflow heat exchanger, the temperature profiles will simply become a parallel straight lines. Then delta Ti is equal to delta Te. Okay. So LMTD definition and how to calculate this. Remember, in the heat transfer entire subject, this is the easiest chapter. If you get a question, they are lucky. Immediately first attempt this heat exchanger, because LMTD method is always meant for calculating the area only. To design, it is a LMTD method means it is all about the design of heat exchanger, getting the area, just finding out the area. Whereas in effectiveness NTU method, what is the main, when do you go for this effectiveness NTU method? Only when two temperatures are given. In any heat exchanger problem, if you are reading three temperatures there, yes, go to the LMTD method. If you are only reading the two temperatures, whether THI or TCI, like that, and both the exits are not there, THE and TC are not there, then go to the effectiveness NTU method. And the special cases formula you have to remember. Special cases means when one of the fluids is undergoing phase change, then LMTD of parallel flow, counterflow, cross flow, all will be the same. Okay. When supposing one fluid is undergoing phase change, like in steam condenser, effectiveness of the counterflow and effectiveness of the parallel flow, LMTD of the parallel flow, LMTD of the counterflow will become same. So it does not matter what type of heat exchanger you are going to design. It doesn't matter what type of heat exchanger you are going to design. If one of the fluids is undergoing phase change, for example, steam condenser, evaporator, or a steam generator, one fluid is undergoing phase change means its temperature will not be changing, right? So I explained about the typical important areas about the heat transfer. Now let me go to the another important subject called thermodynamics. Thermodynamics, the prime basic thermal engineering subject. In the thermodynamics, before attempting any thermodynamic problem, try to ask yourself 3 questions. What type of system you are dealing? What type of thermodynamic system you are dealing? Whether it is a closed system or an open system or isolated system. Number 1, that is the first inquiry. Second inquiry, what kind of process you are dealing? Whether it is a reversible process or an irreversible process. If it is a reversible, what kind of process is that? Isothermal, adiabatic process, or a constant pressure, or a constant volume, or a polytropic? What kind of process you are dealing? Because there are 5 processes are there: isochoric, isobaric, isothermal, adiabatic, and polytropic. Which process you are dealing there? Which process is undergone by the system? That is the second inquiry. First inquiry is a inquiry about the system, type of system. Second inquiry is the inquiry about the nature of process. Irreversible or reversible? If it is reversible, what type of is that? Isothermal or adiabatic or a polytropic, etc. Third inquiry will be the what is the nature of working fluid, whether it is an ideal gas or not. If it is an ideal gas, problem becomes relatively easy because ideal gas equation is there. PV is equal to nRT or PV is equal to mRT, where this R is different, this R is different. This is a universal gas constant, 8.314 kilojoules per kg mole Kelvin. This is a mass, this is a characteristic gas constant. This characteristic gas constant is universal gas constant divided by molecular weight of the gas, right? So these are all meant for only ideal gas equations. When you talk about the ideal gas equations, you will get many relations. Cp minus Cv is equal to R, Cp by Cv is equal to gamma, etc. Pv is equal to mRT, Pv is equal to nRT. This is a number of moles, number of moles, and this is a mass, m is a mass. Okay, when you write this, maintain the proper units. Pressure must be always, the entire thermodynamics, try to keep the pressure only in kilopascal. Not only in thermodynamics, in heat transfer also, wherever pressure is to be substituted, keep it only in kilopascal absolute. Okay. So if the ideal gas is the thing, relative problem becomes relatively. If it is not ideal gas, like a steam or a refrigerant, things we have to go to the properties of pure substances. We have to pick up the property data from that given table, right? So in thermodynamics, the main important topics, if we just look at, this is SFEE. I can say the number 1 because most important topic is SFE. Very often questions will ask, particularly in the nozzle, particularly a varying, convergent divergent nozzle. Steady flow energy equation, we know delta H plus delta KE plus delta P. Okay, Q is the heat transfer, W is the work transfer. Always right side, this is delta H means H2 minus H1, delta K means V2 square minus V1 square by 2, P means change in potential energy. So this is the question pertaining to the nozzle they are asking very often, and its applications, particularly throttling. Throttling is an isoenthalpy process, right? Throttling is an isoenthalpy process. What will happen during the throttling? Like whether pressure will decrease or a temperature will change or enthalpy will change. What will happen to the entropy? So these things they will ask. And in the very first chapter, if you just look at the thermodynamics, path function, point function, these definitions, Q and W are path functions. All properties are point functions. Okay, property exact differential. This is exact differential. This is inexact differential. Path function, point function, and delta Q and delta W are inexact. are inexact differential, whereas dp, dt, dh all are exact. All are exact differentials. Okay. So, give a more important for a path, which is a heat and work are path functions. They are not the properties. They are the path functions. They are inexact differentials, where all of them are exact. Try to distinguish between the path functions and the point functions. And also the very important first chapter will be Q minus. This is a for a closed system. For a whenever you write the closed system, this is the first law of thermodynamics. This is the first law of thermodynamics written to a closed system. And any system, any closed system, any process you could write. But when you are writing, the precautionary thing is, right side thing will be U2 minus U1. Final internal energy minus initial internal energy. Okay. This is a heat transfer and this is a minus in the equation. Sometimes work say Q is, when is Q positive, when is negative. If heat added, positive. If heat rejected, negative. Similarly, W, positive. You have to sign convention is there, work done by the system. This is work done on the system. Expansion works are work done by the system. Compression, like example, expansion of the gas is a work done by the system. This is a compression of the gas. This is a work done on the system. So you have to first make out this the sign convention for the heat transfer and the work transfer, and accordingly substitute in this first law of thermodynamics. Okay, and I already said first law has got three different formats. Cyclic integral of delta Q is equal to cyclic integral of delta W. This is Q minus W is equal to delta U. And the third format I already written, that is Q minus W is equal to delta H plus delta Ke plus delta Pe. This which is also famously known as steady flow energy equation. Sometimes unsteady flow also means something like a filling of the flask. Sometimes but this case is not that often, but I have seen the questions in the recent gate only. You are filling a flask for a pipeline by opening a valve. Initially it is a vacuum. Initially there is a gas going, some of the gas will enter here. And what is the final internal energy, final temperature? If it is initially vacuum container, but after opening the valve, the gas will enter, and after some time the valve is closed, and then what will be the final pressure and final temperature? This is called as the unsteady flow energy equation. Okay, this is steady flow energy equation, SFE. Three formats of first law. We have to, one question will definitely come in the first law applications. Okay, and incidentally, all these three equations are applicable for any thermodynamic process and any working fluid. The questions on the thermodynamics, they will ask very typically. You will give one equation. Say for example, TdS is equal to du plus PdV. You will give this equation. Then you will ask, is this equation applicable only for the reversible or only for the irreversible, or both any process you can apply, or is applicable only for the ideal gas or only for the steam or any pure substance? So such kind of questions very often come. Actually, in this equation there are 5 thermodynamic properties: temperature, entropy, internal energy, pressure and specific volume. Because this is a relation among 5 thermodynamic properties, this must be applicable for any thermodynamic process undergone by any working fluid. It can be written for a steam, it can be written for an ideal gas like air. Air is an ideal gas. So that distinguishing one must be. There is another equation, TdS is equal to dH minus VdP. This relation also is applicable for any thermodynamic process because it is a relation among 5 properties. Okay, any relation containing properties only is applicable for any thermodynamic process, because the change of a property is independent of the path followed. The change of a property between 2 given end states, thermodynamic end states, is independent of the path followed. Therefore, any process, any working fluid also you could write. But if working fluid, for ideal gas, I have got some extra concession. What is that? For ideal gas, du is equal to Cv dt, dH is equal to Cp dt. The changes of internal energy only for ideal gas. This is the changes in internal energy is proportional to the changes of temperature. Cv and Cp are the specific heats. So, if your ideal gas has got some privileges. This like this. Earlier also written, no? Like this. The ideal gas has got some privileges there, like this. PV is equal to MRT. These are all for the ideal gas, like du is equal to Cv dt, dH is equal to Cp dt. They are exclusively can be used exclusively reserved for ideal gas, because for ideal gas both internal energy and enthalpy depends only on the temperature. For ideal gas, both internal energy and enthalpy depend only on the temperature and not on anything else. Okay. Now, so the first law questions are very common in GATE, particularly SFE, throttling they may ask, steam turbine, very easy. First law application very commonly they are asking the steam turbine, something like you will give the steam, certain mass flow rate, some heat loss may be given. Heat loss means negative, and some steam will enter with some enthalpy, kinetic energy, etc. Steam may leave with enthalpy and kinetic energies. What is the power output? This is a steam turbine. These kind of questions are very often coming, sir. And given the mass flow rate. Mass flow rate of the steam wheel is given in kg per second. You will be calculating what is the power. Just simply write the steady flow energy equation, get the power. Of course, power means what? Work done per second. But carefully you have to take the sign. Because heat is rejected, when you are substituting that equation, we have to give a negative sign here. But this minus does not speak about the W. This minus is the equation, minus sign in the equation. That don't speak about the sign of W. Actually, when you are writing the first law, do not assign any sign for the unknown. That point also we have to very keep. Q minus W is equal to delta U. If Q is unknown, take it as positive only while writing that equation. If the final answer you got as a negative, then you think that yes, because it is a negative, heat might have been rejected. Say Q minus W is equal to delta U. W, we don't know whether work is done on the system or by the system. Do the problem, take it as a positive only, W. And if the answer obtained for the W is negative, then you say that because W answer is negative, work is done on the system, compression work. So that particular precautions you have to keep in mind when you are solving the problem. Of course, that you will get only keep on doing the problems there. Okay. So this is one very commonly observed question in the, or sometimes instead of steam turbine, they may ask you about the compressor. Compressor means here the work output. Obviously W you will get as a positive answer, because here it is a steam turbine, will do the work, will give you the work. Whereas if it is a compressor or a pump, they take the work. Therefore, then in such cases, if W is unknown, you will get a negative answer. Minus sign shows that work is done on the system. And also you will ask about when you can write integral PDV. Integral PDV is only for the closed system. For any closed system, any reversible process. Any reversible process only, quasi-static only. Whereas minus integral VDP, this is exclusively written for a steady flow open system. This is for a steady flow open system. Like pump, turbine, compressor. Pump, turbine, compressor, they are the steady flow open systems. In such case, it is a minus integral VDP. Integral PDV for the any closed system, any reversible process. So that this is the area of the PV curve on x-axis. This is the area of the PV curve on y-axis. But only for one thermodynamic process they are equal, that is isothermal process. For isothermal process, both the works are equal. This is the integral PDV is the area of the PV curve on x-axis. Integral VDP is the area of the PV curve on y-axis. Both these areas will be equal if the process undergone by the system is isothermal. But isothermal process is very rarest process, very difficult to achieve practically, right? Coming to this, another important thing is second law. Main thing in the thermodynamic question means second law of thermodynamics, something like this. A heat engine driving a refrigerator, some source, sink, and some low temperature. Refrigerator function is to pick up the heat from the low temperature and reject it to the high temperature, right? So such questions are very common. A heat engine will be driving a refrigerator. You will give these temperatures or some how much heat is there, Q supplied, Q1. They will ask you to calculate this is Q2, this is Q3. They may ask you to calculate Q4 by giving the COP. So when you talk about the second law, thoroughly get the definitions of thermal efficiency of heat engine, COP of refrigerator, and COP of heat pump. We have to be very thorough with the definitions. And then first law. When you write the first law, see, when you are writing the first law of thermodynamics, the clue is that the sum of the arrows entering the cycle must be equal to the sum of the arrows leaving the cycle. Say for example, if you take this heat engine, which is a clockwise cycle, heat engine cycles are always clockwise. So this is entering, this is leaving, this is leaving. Therefore, this should be the sum of this work plus this heat rejection. When I say arrow, it includes all the energies, W and Q both. When you write the first law for the refrigerator, this arrow is entering, whereas this arrow is leaving. So the sum of these two should be equal to this. For the refrigerator, Q rejected should be the sum of work input plus heat extracted from low temperature. Refrigerator extracts heat from the low temperature and reject it to the high temperature. It is run by external work input. Sum of these two is this, that is first law. And definitions, thoroughly learn them, okay. And another important thing, first law is the Carnot. Questions on Carnot cycle and Clausius inequality. Clausius inequality, that is cyclic integral of delta Q by T is less than or equal. Its applications. Give a more focus on the Carnot cycle. Second law applications mainly you see in the Carnot heat engine and also in the Clausius inequality. Clausius inequality is the corollary of second law of thermodynamics, byproduct of second law of thermodynamics. Why there are two signs, less than sign for the irreversible cycle, equality sign for the reversible cycle, and applicable for both clockwise heat engine cycle and as well as the anti-clockwise. Anti-clockwise cycle means refrigeration and heat pump cycles are anti-clockwise cycles which they require the work. Anti-clockwise thermodynamic cycle means that cycle is run by taking the work. Clockwise cycle means it gives you the work. Here all the heat engine cycles like Otto cycle, Breton cycle, they are all the heat engine cycles which will give you the work. So this is a certain important area where you have to take about the second law, and of course entropy. Entropy and entropy changes. Entropy changes during a thermodynamic process, and of course that will be done by integrating this equation. Right? Changes of entropy, ds can be taken, T can be taken here, it can be integrated. Entropy changes undergone by ideal gas, what is the difference between reversible adiabatic and irreversible adiabatic? What do you mean by isoentropic? All that will think, and what is the entropy changes of the universe? See, most of the thermodynamic questions in GATE, they don't ask you to calculate the entropy change of a system or the surrounding. Rather, they will ask for the entropy change of the universe. What do you mean by universe? The sum of system and the surroundings put together is called as the universe. System plus surroundings put together is known as the thermodynamic universe. The changes of the thermodynamic universe they will ask. System entropy, during a thermodynamic process, system entropy may increase or may decrease. Entropy of the surroundings may increase or decrease. But if you add these two algebraically, the entropy change of the universe, what you get to know, it will always be greater than 0 because entropy of the universe will never decrease. Entropy of the universe will never decrease. Either it remains constant if it is a reversible process, it will increase if the process is irreversible. So, they give a more focus on the entropy changes there. Entropy change, second law is the main heart of the thermodynamics. Second law, its applications, Carnot cycle, Carnot refrigerator, Carnot heat pump. Remember, reversible refrigerator and the Carnot refrigerator both mean the same. If you use the word reversible, means it is using the Carnot refrigerator. Reversible heat pump means Carnot heat pump. What is the COP of the Carnot heat pump? What is the COP of the Carnot heat engine? Prepare a notes there, small notes. And what is, supposing if it is an irreversible heat pump is there, irreversible, then how to calculate its COP? See, the reversible refrigerator, which is also a Carnot refrigerator, when you calculate COP, we just need the temperatures. But when you calculate the COP of the irreversible refrigerator, temperatures will not be sufficient. We should know how much heat is extracted, how much heat is rejected. All these things must be there for calculating the COP of irreversible refrigerator. For calculating the COP of the reversible refrigerator, just the temperatures itself will be sufficient. Right. Now, this is another thing and the properties of pure substance. This is the slightly tougher topic, properties of. Why it is slightly tougher is because we have to take the data from the table. You will be given a data. Table data will be given along with the question. Saturation pressure, saturation temperature, all the HF, HFG, HG, like that, SF, SFG, SG, VF, VFG, all this data will be given. All this data will be given. And they will ask you to calculate either the heat transfer or work transfer by picking up the data. And here comes, here how the variation of the, as the saturation pressure increases, saturation temperature also increases. So, latent heat definitions, latent heat is HFG, which is nothing but the Hg minus Hf. What do you mean by saturated vapor? What is superheated vapor? Very important thing I want to tell you. If you learn the properties of pure substances thoroughly, this chapter, another big chapter called refrigeration and air conditioning, that becomes very easy. In the power plant, there is a R&AC chapter, in the power plant engineering stream. That refrigeration air conditioning chapter will become easy only if you thoroughly understand these properties of pure substance. If you prepare this thoroughly, that another subject will become very easy. And here there is another relation also he is asking very often recently, Clausius-Clapeyron, Clausius-Clapeyron equation. This will give you the dP by dP saturation temperature. No? The variation of the saturation pressure with saturation temperature is given by this Clausius-Clapeyron relation. Okay, that is also recent gate exams it is being asked actually. And triple point definition, sublimation and a TS diagram. When you talk about the properties of pure substances, you will be seeing the TS diagram of the pure substance. And unless you know this one here, if you properties of pure substances, if you learn it thoroughly, the analysis of the Rankine cycle, analysis of the vapor compression refrigeration system, all that will become easy. So, give a more focus on this. It's slightly tougher chapter. It is not as easy as that of the ideal gas. Ideal gas problems are easy because we have a definite relations. We don't have to refer to the tables. But here we need to refer to the tables and pick up the data and solve the problem. Okay. So, this is a TS diagram for a isobaric process on a temperature entropy diagram. And lastly but not least, that is the available energy. Available energy, that is easy only, available energy or energy or availability concept. Okay. It is a maximum useful work obtained from a heat engine, assuming that sink temperature as that of the environment. When you talk about the available energy and availability function, the important things is the ambient temperature. In the same chapter, you read also Irreversibility during a thermodynamic process can be directly calculated by using this formula, where T naught is ambient temperature in Kelvin, always in Kelvin. Delta S is the change in entropy of the thermodynamic universe. So, and availability, irreversibility, supposing when you talk about the available energy, if you are giving certain heat source at certain temperature, the lowest temperature of heat rejection is that of the environment. This part is the unavailable energy. This is the unavailable energy. This part will become the available energy for a given heat supply. T1 is the source temperature. This is the source temperature. But the sink temperature should be that of the ambient. T naught symbol is always reserved for the ambient temperature. So in the thermodynamics, if you ask me what is that area where you have to focus more, means second law and entropy. Second law and entropy. The entropy of the thermodynamic universe will never decrease. The entropy change during any thermodynamic process can be calculated by knowing the initial state and final state. There is some thermodynamic process 1 to 2. We don't know whether the process is reversible or irreversible, but if you are having the pressure, specific volume, temperature data at the initial state and at the final state, yes, we can calculate the change of entropy by integrating that equation. TdS is equal to du plus PdV, TdS is equal to dH minus VdP. By integrating that equation, we can calculate the change of entropy without knowing the nature of the process, whether it is reversible or irreversible. Okay? So this is all about the thermodynamics, and going to the another power plant RAC IC. All he has put in one stream, one chapter in in GATE syllabus. As far as IC is concerned, only the cycles give the importance: Otto, diesel, dual, Breton. Only cycle analysis, thermal efficiencies and thermal efficiencies, compression ratio, cutoff ratio, pressure ratio, all these things. Pressure ratio you will see only in the Breton, and how to represent it on a TS diagram and PV diagram. Focus more on that IC. When you talk about the power plant, actually only two power plants only they will ask. One is the steam and the gas power plant. When you talk about the steam, Rankine cycle analysis, and this is relatively easy. This is the Breton cycle analysis. When you talk about the Rankine, they will ask about the modifications. They don't ask much about the Rankine cycle, rather they will ask about the modifications. Modification means when you provide the regeneration, what will happen to the mean temperature of heat addition. Mainly the question comes T mean, that is the mean temperature of heat addition. If this increases, the thermal efficiency of the Rankine cycle will increase. Any action if you take that would result in the increase of mean temperature of heat addition will automatically result in increase of the thermal efficiency. And he may give you that property because it is steam is a pure substance, it is not ideal gas. They will give all the data, boiler pressure, condenser pressure, in that they will give all the property data in the question. They will ask you to calculate thermal efficiency, net work done divided by heat supplied, that is turbine work minus pump work divided by heat supplied in the boiler. So pump work most of the times they neglect, but pump work you can calculate from integral VdP. V is a constant for the water, V into boiler pressure minus condenser pressure. From this we can calculate the pump work, which is a very small, negligibly small as compared to pump work is far lesser than the turbine work, not even 2 or 3%. Just 2% of the turbine work, 2 or 3% of the turbine work will be used to drive the pump here. So that kind of analysis we have to Turbine, this is the work of pump. Here what you get is the work of turbine. Okay, try to make a Rankine cycle questions were repeatedly asked. See, in the power plant RAC IC, the most of the questions come from in the Rankine cycle and its analysis. In the recent exams, I didn't find much questions about the RAC, but on refrigeration and air conditioning. But if you talk about the RAC, only give attention to the VCR cycle, vapor compression, refrigeration cycle. Simple dry saturated VCR cycle. Simple dry saturated VCR cycle, try to give the attention. Here this is a condenser pressure, here it is an evaporator pressure. Vapor compression refrigeration cycle, you try to analyze, that will be sufficient. COP. Main thing is how to calculate the COP. Refrigeration effect. What is COP? Refrigeration effect divided by work done. What is the tonnage? Tonnage capacity of the refrigeration system will be mass flow rate of the refrigerant into refrigeration effect divided by 210. It should be in kg per second. It should be in kilojoule per kg. Okay. 1 ton means 1 ton refrigeration means 210. Okay, 1 ton of the 50 kilocalories per minute or 210 kilojoules per second. 1 ton means 50 kilocalories per minute. Sorry, actually here this is kg per minute. Or 210, 50 into 4.2, 210 kilojoules per minute. Or 3.5 kilojoule per second. This mass flow rate should be in kg per minute. Tonnage capacity. And main thing about the air conditioning, when you talk about the air conditioning, only psychrometry only you try to give the more specific. Psychrometry means psychrometric properties, psychrometric chart. We have to thoroughly have the idea about the psychrometric chart. DBT, specific humidity, WBT lines, RH lines. These are all the RH lines, right? These are all the relative humidity lines. Here the RH is 100% saturated curve. So you should be able to read the psychrometric property. You should be able to read the psychrometric property any psychrometric property from the psychrometric chart. This is 90%. This phi is all are relative humidity curves. These are all the relative humidity curves. These are all the wet bulb temperature constant. So main thing DBT definitions we have to thoroughly WBT, DPT, dew point temperature. Okay, and we should be able to read the psychrometric chart, and very importantly the psychrometric relations. 0.622 into PV by PB minus PV. This is the relation for specific humidity, and RH has got PV by PS. Yes, these two most of the questions asked in the gate, they are about only these two relations. This PV and for that we should very cleverly able to read the property data, pure substance. I already said, once you thoroughly understand the pure substances chapter, once you thoroughly understand the pure substances chapter in thermodynamics, two other chapters will become easy. One is refrigeration and air conditioning, this one, and another thing is the Rankine cycle analysis in the power plant. If you thoroughly learn the properties of pure substances in thermodynamics subject, that would help you very much in understanding refrigeration air conditioning and also the Rankine cycle and its applications in the power plant engineering. So one chapter in one subject is very much needed to understand the two different subjects. One is power plant and other is refrigeration and air conditioning. Here why I am telling is, this saturation pressure, PS, is taken at the DBT, dry bulb temperature, which is given in the table problem. This corresponding to this PV, if you read the saturation temperature, it is a dew point temperature. So this table, if you remember this table, these two relations can be easily done, and most of the gate questions they will ask about either specific humidity. What is phi? Relative humidity. Phi is the relative humidity, RH phi. Actually, you may expect around 5 marks in the power plant, IC and R&DC put together. You may expect around 5 marks, not more than 5. One question may come in the Rankine cycle, and in the IC engines you don't see anything except about the cycle analysis, Otto cycle, diesel cycle, dual cycle, and what is the influence of increasing compression ratio on the efficiency, increasing the cutoff ratio. Cutoff ratio you see only in the diesel cycle. Okay, RC both you will see in the diesel cycle. In the Otto cycle you will see only the compression ratio. But when you come to the Breton cycle, you will see the pressure ratio, RP. So when you change this pressure ratio or a compression ratio or a cutoff ratio, how their efficiency will change, that you try to remember. And try to calculate what is the heat supplied, what is the heat rejected, but from the basic thermodynamic relations. See, as I already said, in the first chapter of thermodynamics, you will learn about the work done, heat transfer in various thermodynamic processes. 5 processes are there. Prepare a table for all the 5 processes: isochoric, isobaric, isothermal, adiabatic, polytropic, and how to calculate the heat transfer in each process, how to calculate the work transfer in each process. Try to remember the formula. And for if the work done, if the working fluid is ideal gas, for any thermodynamic process you could write this, right? This delta H is equal to MCP delta T, delta U is equal to MCB delta T. They hold good for any thermodynamic process. Hold good for any thermodynamic process, reversible or irreversible, isochoric or isobaric or isothermal, undergone by ideal gas. Condition is only ideal gas. Ideal gas means, example, air. Ideal gas like air. Air you can treat it as an ideal gas. Of course, for real gas, this equation is there. P plus A by V square into V minus V, B is equal to RT. This is a van der Waals equation of state for real gas. Van der Waals equation of state for real gas. If A is equal to 0 and B is equal to 0, that will become the ideal gas. This is for the real gas. What is the equation for the ideal gas? PV is equal to MRT. Okay, PV is equal to MRT. This is the ideal gas equation, that is the real gas equation. But real gas tends to behave like ideal gas at very low pressures and at very high temperatures. The behavior of the real gas will become equal to that of the ideal gas if the pressure is very low, as P tends to 0, and if the temperature is very, very high, as T tends to infinity. Real gas will become to the ideal gas. In such case, A will be 0 and B will be 0. If P tends to 0, and T tends to infinity, ideal gas and real gas become equal. Real gas almost becomes ideal gas. At very high vacuums, as P tends to 0 means at very high vacuums. At very high vacuums and at very high temperatures, T tends to infinity. T tends to infinity. Real gas will become ideal gas. So this is a real gas equation, van der Waals equation of state for the real gas. So try to learn more in the pure substance. Ideal gas relations are quite easy because Like this. See, any thermodynamic process undergone by ideal gas, we can use these two relations. Prepare first table for that 5 processes, Q value, W value, changes of entropy. All the thermodynamic processes can be seen in one table. Prepare one table, heat transfer, work transfer, change of entropy, change of internal energy, change of enthalpy. Then if you just keep referring to that table, supposing if you are given a what is the work done by reversible adiabatic process, means P1 V1 minus P2 V2 by gamma minus 1. If it is a reversible polytropic process, P1 V1 minus P2 V2 by n minus 1. So that is all for the only for the closed system. See, all those relations for the closed system. Integral PDV is the formula for the work done by a closed system during a quasi-static or reversible process. So which process, what formula must be used to calculate the work? Integral PDV, if you want to write, two conditions must be satisfied. System must be closed and process must be reversible. If you want to write integral VDP, two conditions must be satisfied. Number 1, it should be steady flow open system. Number 2, process must be reversible. Okay, so this distinguishing we have to keep while preparing a short notes. Thermodynamics is, that is why people feel the thermodynamics is a bit tougher, because what process, what working fluid, what system, particular equation is valid. Say for example, look at this. This is these two are valid for any thermodynamic process, for any thermodynamic system, but the gas must be ideal. This is, then only you could write these two. They are valid only for the ideal gas. If it is a refrigerant, can you write? No. If you write, if it is a steam, can you write? No. But for refrigerant steam, how do you get then? You have to use the tables. You have to use the tables, properties of the pure substances, because they are pure substances. Pure substance is a big set, out of which one subset is the ideal gas. Ideal gas is also pure substance, but ideal gas has got certain privileges, certain relations. PV is equal to MRT, PV is equal to nRT, du is equal to CVDT, dH is CPDT, like that. Okay. Now this is all about the thermal stream. Now coming to the mechanics and design, applied mechanics and design stream. The first chapter will be the engineering mechanics, EM. See, when you talk about the engineering mechanics, give more attention to the dynamics part and how to make use of the work energy theorem, conservation of linear momentum, collisions. When you talk about the conservation of linear momentum pertaining to the collisions chapter, okay, coefficient of restitution, work energy theorem, free body diagram, which the main thing is how to construct the free body diagram, and friction related problems. And the questions mostly give the more focus on the dynamics part rather than the statics. Generally weightage will be 4 marks, 3 to 4 marks in engineering mechanics. But generally people fear about engineering mechanics because they have studied in the very first year of engineering. Okay, but try to read the very good books like Beer and Johnson. In the last minute reference also, sometimes they will help you. Beer and Johnson or Timoshenko and Young. Those books are quite helpful in solving the problems of the engineering mechanics. Then comes the strength of materials, SOM, mechanics of solids. Actually, this is the main subjects. You may expect up to 7 to 8. You may expect around 7 to 8. Because this is important. If this is learned, automatically you will be proceeding to the design of machine design. Automatically machine design becomes easy, because machine design is a practical application of the strength of materials. Like properties of pure substance is useful in the R&D and power plant. In the similar manner, if you learn this strength of materials thoroughly, automatically the other chapter in the applied mechanics division, machine design, also becomes easy. Some very first chapter, the good number of questions are asking elastic constants, Hooke's law, that is Young's modulus, bulk modulus, shear modulus, Poisson's ratio. What is new? Poisson's ratio, lateral strain by longitudinal strain, and you know that, and the relations among the four E is equal to 9 kc by 3k plus c, like this. E is equal, elastic relation 9 kc by 3k plus c. Okay, Poisson's ratio, E is equal to 2k into 1 plus 1 by m. E is equal to 2k into 1 plus 1 by m, where the 1 by m is the Poisson's ratio. So these relations and but particularly this stress strain diagram of a mild steel, the stress strain diagram of a mild steel, what is this area represents, what is the various points, elastic limit, upper yield point, limit of proportionality, elastic limit, upper yield point, lower yield point, ultimate strength, breaking point, all these points you have to thoroughly learn this. Stress strain diagram for the mild steel. Okay, and proof resilience. Try to learn the proof resilience or modulus of resilience. Strain energy, most of the questions in first chapter they asked about the strain energy. Strain energy stored up to the elastic limit per unit volume is called as the proof resilience or modulus of resilience toughness. And the stress strain diagram entire area, the stress up to the breaking point, this is the breaking point, this is ultimate strength, upper yield, lower yield, elastic limit, limit of proportionality. Everything we have to give a more focus on this very first chapter, and elastic constants, relations among themselves. Okay. What main thing, strain energy, give a great focus. What is the strain energy? First of all, if you have a spring, if you elongate the spring, that means by doing some work, whatever the work you have done, that will be stored in the spring. When you release the force, the spring would be able to do some work. In the similar manner, when an elastic member is with the application of the external loads undergoes deformation, there will be some energy stored within that member due to the deformation. Okay, that energy stored within the member is called as the strain energy. The energy stored inside the member by virtue of the strain undergone by the member is called as the strain energy. Half into stress into strain, that is the formula for the strain energy. Give more focus on the strain energy and that proof resilience, modulus of resilience, toughness, those definitions. What is the link? Give a deep insight into the stress strain diagram of the mild steel, and try to learn about the properties also, that elastic property, like all that material properties, which is again useful in the material science. Material properties are required in the material science and also in the machine design, right? Ductility, malleability, proof, and all these properties one must be very thorough, particularly in the machine design. Okay, right, then another important, I give the most important weightage to the principal stress and strains and Mohr circle. If you understand the Mohr circle thoroughly, we can ask many questions in the strength of materials and machine design. And before going to the principal stresses, first take a stress element which is generalized to direct stresses, both may be of tensile, and one shear. Okay, this is tau. So for this particular kind of a case, on any element, on any plane which is considered at an angle of theta, how to calculate the normal stress and the tangential stress, that formula we have to remember. And what is meant by principal plane? What is the principal stress formula? What is the principal plane? How to construct the Mohr circle? In the Mohr circle, x-axis is always a normal, right? Y-axis is for the shear. This is for the normal, this is for the shear. How to construct the Mohr circle? And some special cases will be there. When an element is subjected to the only pure shear, when an element is subjected to only pure shear, no direct stresses are there, it is a pure shear, right? Pure shear case, when did you see? Again in the torsion. A shaft subjected to a torsion or a twisting moment, if you take a small element there in that, that is subjected to the pure shear, right? If you take an element in the shaft of a member which is transmitting power, subjected to a torque or the twisting moment, obviously that is subjected to the pure shear. For that case, if you construct the Mohr circle, it will be at the center of the Mohr circle. Here, this is the Mohr circle for that pure shear. And if you learn these principal stresses and principal strains, what is the principal plane first of all? It is the plane on which there are no shear stresses. The only normal stresses that are existing over the principal planes are called as the principal stresses. And there will be two such principal planes located at 90 degrees. And sometimes the element may be subjected to some compressively. For example, one may be tensile, other may be other direct stress, normal stress will be of compressive nature. So for all such variations, you should be able to construct the Mohr circle there. You should be able to construct the Mohr circle. What is the radius of the Mohr circle? Okay. What is the formula for calculating the radius of Mohr circle? When that radius of Mohr circle becomes 0, for a fluid element, I just give them an example. A fluid element under rest, fluid element at rest. What is the radius of the Mohr circle? Because it is subjected to the equal normal stresses, that too of compressive. Why compressive? It is a hydrostatic pressure. The pressure acting over all the sides is same according to the Pascal's law. According to the Pascal's law of hydrostatic pressure, a fluid element under rest is subjected to the same compressive stress in all the directions. A fluid element at rest is subjected to the same compressive stress or the same hydrostatic pressure in all the directions. I can say other way also. The pressure at a point in a static mass of a liquid is uniform in all the directions. The hydrostatic pressure acting at a point in a static mass of liquid is uniform in all the directions. So in such case, what is the radius of the Mohr circle? Radius of Mohr circle becomes 0. Is 0. That means, what is if you draw the Mohr circle, this is sigma, this is shear, this is the Mohr circle. This is the Mohr circle. Mohr circle shrinks to a point. This is the Mohr circle. This is of compressive nature. Why on the negative side is taken? It is of compressive nature. This is of compressive. No? Hydrostatic pressure is compressive in nature. That is why on the negative x-axis he has taken. This is the positive x-axis. This is a negative x-axis. This is the Mohr circle for this element. This is the fluid element at rest. Such kind of questions will be asked in the gate. And another, main thing is principal stresses and strains and the application of the Mohr circle. And this will be very much useful to understand the theories of failure in the machine design. Maximum principal stress theory, maximum principal strain theory, maximum shear stress theory, like Rankine theory, Trescos theory, von Mises theory. No? So all these theories of failure will be understood only when you understand what is the principal stress, what is the principal strain, and where do that principal plane lies, where do the principal stress, how much will be the maximum principal stress. So all these things one must be very, very thorough to understand the design problems. Okay. And again, bending moment, BMD and SFD, shear force and bending moment diagrams. Okay. Point of counterflexure. Okay. And what are the conditions, like these equations? dm by dx is the shear force, ds by dx is the rate of loading. how to construct a bending moment diagram for a simply supported beam for any kind of a loading. Maybe a part will be UDL, a part may be a point load, like this, like that kind of a problem. So where do the shear force change? Where is the shear force change sign? Bending moment will be maximum where the shear force changes its sign, or shear force becomes 0. Okay. So where is the bending moment will be maximum, where is the bending moment will be 0, and what are those points are known as. These are the things we have to be very, very thorough. And finally the bending moment equation, m by I is equal to F by Y is equal to E by R. These are the direct stress actually. I is the area moment of inertia, E is the Young's modulus, what is the R is the radius of curvature, and M is the bending moment, and F is the direct stress, and Y is the distance measured from the neutral axis. This is neutral axis. So these things, the bending moment equation, how to make use of the bending moment equation, what is that E and I, flexural rigidity, and all these things. Okay. SFD, BMD, and the bending moment equation and its applications in the problems pertaining to the design of beams. Okay. And the easiest chapter is what I can see is torsion. Similarly, corresponding to the bending moment equation, this is a torsion equation like this, where IP is the polar moment of inertia and F is the maximum shear stress, which you see at this. A shaft is subjected to a twisting moment, right? Where is the shear stress will be maximum? On the surface. R is the radius of the shaft, C is the shear modulus, theta is the angle of twist, and L is the length. So the questions on this design, because this is very much required in the design of the shafts. Okay. And of course deflection of beams, slopes and deflections of beams. And you have to remember the formula, how much will be the deflection. Suppose a cantilever is there, is subjected to a point load. Okay, how much will be the deflection in terms of the W and length and moment of inertia, etc. Okay, they will ask if the moment of inertia is increased, what will happen to the deflection. The questions will be asked like that. If the magnitude of the moment of inertia is increased, if the material is same but the moment of inertia is changed, how do the deflection will change? Such kind of questions will appear. But easiest chapter in the strength of materials, I can say, is the first chapter. Elastic constants and definitions, basic definitions, how to calculate the deformations in the composite shafts. Okay, and I can say the toughest chapter will be the deflection. Torsion is easy. Principal stresses is important and slightly difficult, principal stress theory and Moore circle, because that is required again in the machine design. And when you talk about the theory of machines, actual weightage is around 8 marks, around 7 to 8 marks. And again here also velocity acceleration diagrams, give a more stress to the velocity acceleration diagrams and planar mechanisms, Slater-Kange mechanisms analysis. Here the maximum number of questions come. And of course vibrations. One question guarantee will come. One question guarantee on the vibrations. Velocity acceleration, instantaneous center methods, and all these things, you will see planar mechanism, Slater-Kange mechanism analysis, and all these things are very important in the theory of machines, apart from the vibrations I am talking. And of course cams are relatively easy. Cams, governors, they are relatively easy. Machine design, main thing machine design, what you have to learn is theories of failure. Theories of failure, the 5 theories, 5 theories are there. Rankine theory, Tresca's theory, von Mises theory, all these which are also called as the maximum principal stress theory, maximum principal strain theory, maximum shear stress theory, maximum strain energy theory, distortion energy theory. So all these, only 5 are there. We have to understand which material, which theory is applicable. That is how the questions will ask. which kind of material, which theory is, whether a ductile material, which theory is available, brittle material, which theory is available. So, and 5 theories of failure and their application, practical applications where you can write. That is the main thing in the theories of failure. One question will definitely come in this arena. And design of shafts, keys and couplings, that is also, but actually to understand this machine design, one must be very good thorough at the strength of materials. If a SOM is, you are thorough at the SOM, automatically you will be good at the machine design also, because this is an application of that, practical application of that. Coming to the manufacturing and industrial, I can say the most important topic is the orthogonal turning, where the questions very often come. Compulsorily it will come, one question will come, 2 marks question. Orthogonal turning, where you talk about the AS system, merchant circle, machine tool dynamics, Taylor's, this year Taylor's tool life equation has asked. Taylor's tool life equation. This is the most important chapter, metal cutting and machine tools. Metal MCMT, which we call machine tools, metal cutting and machine tool engineering. Drilling and all this, drilling, boring, and how to distinguish them. Supposing if you want to drill a hole inside a shaft, which operation is followed by another one actually? That kind of a questions will be asked. They were asked in the recent gate also. And machine tool dynamics is the orthogonal turning dynamics, mechanics of the orthogonal turning, rake angle, shear angle, and shear plane, and how to calculate the relevant parameters by using the Taylor's tool life equation, merchant circle, etc. Give a more focus on that. 1-2 marks question is definite in this area, orthogonal turning or orthogonal cutting. Okay, but because it's something like a mathematical, you have to construct the merchant circle and do the analysis. And another thing is there regarding the casting there. In the casting, most important thing is solidification time. They ask very often solidification time and casting defects, runner riser design. By using the, again you have to use the Bernoulli's equation here, runner riser design, and that and solidification time, casting defects. These are the very prominent areas where the questions will be asked in the casting. And in the welding, most commonly they ask the voltage or arc characteristics. Voltage arc characteristics. That is a very important topic in the welding there. Casting, welding, forming. Actually, they are all put in one particular chapter, right? Casting, welding, and forming. These are all, but they are all put in the one particular chapter. Casting, forming, and welding there. And then we have got the SIM, computer integrated manufacturing, and recently the 1 or 2 marks are being asked in the SIM there. When you come to the operation research, actually in the industrial engineering we have the PPC, OR, and inventory, right? Of course, in the inventory means only main thing is economic order quantity. They focus more on that. In the operation research, it is a very one question in definite in linear programming, apart from the CPM PET. Actually, in the industrial engineering and like PP, production planning control, inventory control, and operation research, you will be getting around 5 marks. These three put together, you may expect around 5 to 6, not more than that. Out of which 2 marks questions will come from the one from the OR, one from the inventory, and one from the production planning and control. Actually, see, the idea of this video is which areas you have to focus more, which areas you have to revise very often in this 1 month. And in this 1 month, what I suggest you to do is, you select a subject and tick off tick mark those important topics. Very oftenly, the most likely the questions will be asked. And that topic you make into 2 or 3 subtopics. Say for example, heat transfer is there. Conduction they will ask about minimum, they will ask about 3 marks say. You break it into 2 or 3 subtopics. One is heat generation case, one is a critical radius case, one is a first thing composite wall with convection. So when you make when you divide that particular topic in 2 or 3 subtopics, so studying becomes easy, making the notes becomes easy, revising also becomes easy. In the final hours revision, that also becomes easy. And like that, say fluid mechanics is there, you select the kinematics. Kinematics is the most important chapter. In that, what are the, again, try to focus on those areas where the questions will be definitely asked, like equation of the streamline. N number of times the questions will come how to find the equation of a streamline for a given fluid flow with a given flow field. And mathematics is relatively easy. As far as the mechanical engineering is concerned, mathematics is relatively easy. That though don't at least though out of 13 marks, you should be able to bag minimum of 8 to 9 marks with a reasonable preparation of the mathematics. Minimum 7 to 8, because out of that 28 marks, if one gets about 20, and remaining all the 72 marks, if you are getting say around 30 or 35, you are sure of getting a very good rank in the gate. If the overall score is around falling between, out of 100, if he is falling between 55, 45, 55 and 45 to 55, you are sure of getting a good rank. But main marks, 28 marks out of 28, you should not lose more than 8 or 9 marks. Minimum you should get 18 to 20. And another 25-30 marks out of the 72, with a reasonably good preparation, if you plan for the around 35 to 40, that 40 plus 20, 60 marks means it's a very good score. Even the topper, All India topper in GATE would not get more than 75. Of course, that depends on the type of depth of the paper. Last year, ISC Bangalore has conducted. This year, like rookie, and and try to look those areas which was conducted by the same IIT last time. That may give you some useful insights into the predicting the paper. So prepare a short notes by dividing that subject into subtopics and then into subtopics. And the entire, say for entire FM, you can make it into 4 or 5 pages, maximum 4 or 5 in the short notes. For maximum 5 pages, you can make 5 long pages or 4 long pages. And but to keep looking at those formula, relevant formula, and what are the mistakes you may commit, that also try to do that. And anyhow, we are conducting some test papers here, try to attend them. And this is because with all my experience, what I say is, never try to commit the mistakes in the exam. But how do you judge that? Pick up the easiest question what you feel first. Just have a quick reading, pick up that question, and generally everybody will be having some favorite subjects. Pick up those subjects. Each student will have certain favorite subjects. First go to those subjects. And because that is a favorite subject, automatically your mind also will be tuned to easily adapt to that question. And because I like some subjects and some other guy may like some other subjects. But because mechanical engineering is a very big chapter, very big branch, we have around 13 to 14 subjects there. And some subjects may be relatively easy as compared to that. In that subject, again, some chapters may be more easy. You are very lucky enough if you do get the questions from that same subject which you are most favorably keep reading often. Okay. So with this, I would like to congratulate. I would like to say best of luck to all of you, and don't waste even a day. Okay, don't waste even a single day. Actually, okay, day wasted is again it will cost your GATE score. And keep referring very often. And I am giving my mobile number also. My name is Sekhar. I have been into this GATE coaching for more than 25 years. This is my mobile number. You may contact me very often because I have got vast experience across India at various GATE coaching platforms. Most of the people who are there in the gate coaching business now, many of them were my students earlier. Okay, so you may contact me if you have any doubt. You are welcome to contact me. So, all the best, dear students, for the last month preparation. Good luck. Thank you.